Okay, good afternoon, ladies and gentlemen. We are going to start with the last lecture of the GLM course. And today we are going to generalize the logistic regression model. That's basically what we are going to do. And we are going to see different models today that are going to help us to do this generalization. Now, in logistic regression, we have an outcome y, which is essentially binary. So we have an outcome, and our outcome can take only two values. Um, Success, what we have over here, and failure. So these are the two possibilities we have when we are dealing with a logistic regression model. Now, sometimes you may have an outcome that can take more than two categories. You may have an outcome that essentially can take J different categories, and J obviously larger than 2, because if J is equal to 2, you're back to binary. So you can only have two possible outcomes, success or failure. But let's assume that you have an outcome J in which, for instance, you are using a new drug and your response variable Y can be worsened, status quo, improve, cure. For instance, in that case, your response variable Y is now a categorical variable. Doesn't take just two values, success or no success, but the patient can worsen, can stay the same, can improve, or can cure. When you have only two outcomes, when J is equal to 2, then you're back to the classical logistic regression model. In that case, you can model the log of odds of an event. And what is the odds of an event? Well, that's what we have over here, is the probability that the event will happen, that's my numerator, divided by the probability that the event will not happen. So the probability that Y will be equal to 1 divided by the probability that Y will be equal to 0, and that, of course, for given values of the covariance. And that's the odds. That's the odds of success for a given value of the covariance. And what we do in logistic regression is we model the logarithm of the odds. That is the expression we model. And this is just what we call the logic transformation of the probability of success. What is the logic transformation? Is the logarithm of the odds. By the way, the probability of y equal to 0 is 1 minus the probability of y equal to 1 because we only have two categories. So j is equal to 2. And one of the two events is going to happen when you carry out a trial. Then that's the classical logistic regression. And by the way, this vector x that we're putting over here is just a vector of covariance. We have a p covariance, so p minus 1 covariance if you consider that x1 is just the intercept, it's just a constant equal to 1. Now, when you have more than two categories, then you can construct j times j minus 1 divided by 2 odds. So here you can construct only one because you have just two possible outcomes. But if you have j greater than two categories, then you can construct j times j minus 1 divided by 2 logits of the odds. However, only j minus 1 are not redundant. So all the others can be obtained. If you model j minus 1, you can obtain all the others. Only j minus 1 of them are not redundant. Now, the logistic regression model was basically was based on the binomial distribution, and these extensions we are going to study today, they are based on a multinomial distribution. A multinomial distribution is an extension of the binomial distribution. What is the multinomial distribution? Let us assume that you have now n trials, and that at each trial, at each of these independent n trials, you measure an outcome, and this outcome can have j different categories. By the way, we are going to assume that j is larger than 2. If j is equal to 2, then we are back to the binomial case. So you have n trials, and at each trial, you measure an outcome, and you may get j greater than two possible outcomes. For instance, if you are tossing a coin, then at each trial you can get only two outcomes. You can get a success or failure, head of cross, etc. If you're tossing a die, then at each trial you may get 6 different outcomes. You may get 1 point, 2 points, 3 points, and so forth until 6. In that case, you will have at each trial a categorical variable if you consider 1, 2, 3, 6 as different values for a categorical variable. Then let's call pi j the probability that outcome j happens. So in each of these trials, you may have j possible outcomes. Let's call pi j the probability that you will get category j, the probability that outcome j will happen. And obviously, these probabilities are going to sum up to 1 because in each trial, one of these j categorical events is going to happen. So I'm using here a small letter j and then the big letter, the capital letter j. The capital letter j denotes the total number of possible outcomes. So these probabilities, they are going to sum up to 1 because in each trial you are going to get of 1 or 2 or j category. One of these one is going to happen. And now we are going to do something similar we did with the binomial distribution. If you remember with the binomial distribution, what we did is we construct a variable y, which is just the number of times we got successes in n trials. And here now we have more than one outcome. So we are going to call yj is equal to nj is the number of trials out of the n trials, the number of trials in which the outcome j was observed. So for instance, y1 and 1 will be the number of times we got outcome 1 in these n trials. And y2 equal to n2 is the number of times we got outcome 2 in these n trials, and so forth. And then we can just construct a vector with j dimension, and here we have is a variable for each possible outcome. And this vector with y1 is the number of times we got outcome 1 in the trials, y2 is the number of times we got outcome 2 in the trial, and so forth. Yj is the number of times we got outcome j in the trial. This vector of outcomes follows a multinomial distribution with parameters n and pi. Well, n is the total number of trials, and pi is the vector of probabilities, in which pi 1 is the probability that you will get a 1 when you do in each trial, pi 2 is the probability that you will get a 2, and so forth. And of course, the sum of all these yj is equal to n, because you did the trial and you have n trials, so the total number of n can be decomposed the number of trials in which you got a 1, then plus the number of trials in which you got a 2, and so forth. That needs to sum to n. Now, what is a multinomial distribution? A multinomial distribution, which is given over here, a multinomial distribution, which is given over here, is just the probability that you will get certain vector of outcomes. That's it. So the probability that you will get n1 times outcome 1, you will get n2 times outcome 2, and you will get nj times outcome j. That probability is given by this expression over here. You have a constant term here, which is depending on these factorials, and then the product of these probabilities to the power pi 1 to the power 1 pi j to the power nj. And this is a multinomial distribution. So that's a distribution that is going to play a very important role in the generalization of our logistic regression model. Now, you can show that for each component of this vector y, the expected value of yj is n times pi j, the variance of yj is n times pi j 1 minus pi j. You can see that this is a little bit the same as for the binomial distribution, because basically you can think about each of these events, yj, for instance, y1, you can decompose it like the outcome 1 happens, yes or not. So you can think about them to a certain degree as a binomial distribution. But of course, these outcomes over here are going to be correlated. And the covariance between yj and yi is given here. And this is the multinomial distribution, which is a distribution that is going to play a very important role in our extensions of the logistic regression model. Now, how we can introduce now a model, how we can introduce the covariance. And we are going to do a little bit the same we did with the binomial case. In some cases, and this is particularly the case when you have design experiments and when your covariates are basically categorical regressors, in many cases, then you obtain what we call repeated observations. So you have a vector of covariates x, and your vector of covariate can take n different values. You may have x1 and xn. You may have n possible outcomes for your vector of covariates. For instance, if you think about the skin cancer example we saw, I think was when we were studying the Poisson model. There, the covariates were CT. You have two values of CT, and then uh, age. And age was divided in 6 different categories. So in total, you may have 2 times 6. Let's see, was 6, 2 times 6. You may have 12 different outcomes for the vector of covariates. And we are going to assume that at each value of the vector of covariate, we have repeated measurements. So we have ni subjects that have covariates equal to xi. So we will have n1 subject that have covariates equal to x1, n2 subjects that have covariates equal to x2, and so forth. And now we will assume that at each level xi, for a given value of the covariance, the response variable y follows a multinomial distribution. So we are going to assume that here we have yi, this is the response vector for this level of the covariance over here, and yi is y1i, y2i, yji, and that this follows a multinomial distribution with ni trials and vector of probabilities pi of xi. Note now that this vector of probabilities is going to depend on the covariant, the vector of covariant. So at each level of xi, I have just a multinomial distribution, just the same we have here. That's the same type of distribution we saw here. So at each vector of the covariate xi, then I have ni trials, and in each of these trials, I can have a j possible outcomes. And then here I have the vector with the number of times that the outcome was 1, the number of times the outcome was 2, and the number of times the outcome was j. And obviously, the sum of all these outcomes is going to be equal to the total number of trials, which is now ni. And this happened at x level of my vector of covariance, xi. Now, if the data are grouped, so if you have repeated measurements, so for every vector x and xi, you have repeated measurements, you have ni observations with exactly this level of the covariate. If that is the case, then we say we have repeated measurements at this level. So we can denote by yk. Let me use the pen. We can denote by yki is equal to nki, and that's the total number of trials out of the ni trials at this level of the vector covariance in which the outcome k was observed. And this is typically the case when you have, for instance, categorical regressors, when you have repeated measurements. If you have continuous regressors, then it's very unlikely that you will have repeated measurements. In that case, each vector of xi is unique. You don't have repeated measurements. For instance, if you have as a vector of covariance, I don't know, weight, blood pressure, age, I mean, you have several continuous regressors, then it's probably the case that you don't have repeated measurements for the vector of covariance, that every person has a unique combination of age, blood pressure, and weight, etc. In that case, ni is equal to 1, and then the vector, the vector here, yi, is going to be a vector of zeros and 1, and jki is going to be equal to 1, implies that the outcome k was the one that occurs, and 0 implies that it didn't occur. So now you're going to have for every subject, because every subject we have a unique vector of covariance, a vector yi, and these components here are going to be zeros and 1. One of them is going to be 1, indicating for this subject you observe outcome 1 or 2 or 3, the outcome that was observed, and all the other components are going to be equal to 0. That's when you do not have repeated measurements. Okay, so once you have a distribution, and once you have a distribution, now you can construct a likelihood, right? And the likelihood is the probability of observing the data. And you can show very easily that this is the likelihood associated with the model we saw before. So here we have the multinomial distribution. So for every response y, we assume that it follows a multinomial distribution with ni and probabilities that depend on pi. And once you have that, you can write down the likelihood. And what is this beta here? Because we have still not introduced the beta explicitly? Well, beta is a set of parameters describing the relationship between these probabilities over here and xi. As we said, for each level of xi, now we have that the probabilities of outcomes j depends on the vector of covariance. So the probability of observing a one will depend on the covariance. The probability of observing a two will depend on the covariance. And that beta, we are going to see shortly, is the vector that uh, links the probability of observing certain outcome to the vector of covariance. If you calculate the logarithm, then you can come out with the log likelihood, which is a nice sum. We have it over here. That's the log likelihood. And now we can apply all the machinery of maximum likelihood to construct confidence intervals to estimate the parameters. We can use the Holy Trinity, the first two lectures of the course. That's why we put so much time at the beginning in seeing all these mathematical details, because as you can see, they come back again and again and again. So once we have a written likelihood, you can apply all the techniques we saw in the first lecture. Now, it can be shown that all the models we are going to see in the following, they lead to a log likelihood that is concave, and that basically means you can use methods like Newton-Raphson, for instance, to calculate the maximum likelihood parameter estimates. And that's it. So the only thing we need to specify now is the model explicitly. So what is the relationship between these probabilities over here and the vector of covariance? That's what we need to specify. Once we have these probabilities, then we just plug in here the expression that gives this probability as a function of beta, and then we can just apply maximum likelihood. Okay, we are going to consider two classes of models. Two classes of models that are going to be different. The first class is when the response variable, y, the one we have seen there, is nominal. And what that means, there is not a natural order between the categories. So we call it, you know, at each trial you can have j different outcomes, 1, 2, 3, 4, etc. until j, but these numbers do not have any quantitative interpretation. They are just labels, right? So you may consider, I don't know, you may consider an outcome that is, let me see if I can come out with such an outcome. For instance, if your outcome is where certain individual lives, you have Wallonia, you have Flanders, you have Brussels. Well, these are just labeled categories. There is not a natural order. I cannot say that Flanders is better or larger than Wallonia, and Wallonia is better or larger than Brussels. There is not any order in these outcomes. You can code that outcomes, as you can say that Flanders is 1, Wallonia is 2, and Brussels is 3, but these numbers do not have any quantitative interpretation. If that is your case, then you can use something that we are going to call the baseline category model. And that's the first model we are going to see here. The baseline category model is when your response, the different categories are not ordered. Now, of course, in some situations, you do have an order, a natural order in your categories. And this is when your response variable is ordinal. For instance, the example we were seeing before about a patient that received a treatment and the outcome is worsened, the same status quo, improve of cure. Here you have, again, a categorical variable, but you can argue that there is a natural order in these categories, because you can say worsened is worse than status quo, and status quo is worse than improve, and improve is worse than cure. So you have a natural order in your categories. And if there is a natural order between the categories, then we are going to see two different type of models. What we are going to call cumulative models, and what we are going to call the adjacent category models. So for the ordinal responses, we are going to see two models. When the responses are not ordered, when you have a nominal response, then we are going to see one model, the baseline category model. Obviously, the baseline category model can be applied as well when you have ordinal responses. You just will be not in the order, but you can apply a baseline category model when your response is ordinal. It's not optimal because you are ignoring certain information. You are ignoring the order in the categories. And we are going to show via an example that when you ignore the order in the categories, you may lose a little bit of power. That's, of course, a natural results of ignoring information. Okay, the baseline category model. We are going to assume that now we have a categorical variable and that can take j possible outcomes. So the variable y can take value 1, 2 until j, but that these values do not have a quantitative interpretation. They are just labels. There is not a natural order there. And we are going to denote by pi j the probability that you will get outcome j when you carry out your experiment given the covariance. So pi j is the probability that we will observe an outcome equal to j given the value of the covariance. And the baseline category logic model, actually what it does is it models j minus 1 log odds. So now we are going to define a category, which is going to be the reference, that the baseline category. That's why we call the model the baseline category model. You choose a category that is going to be your baseline, your reference. Here, and we will discuss a little bit more about that later, we are considering the last category as the reference. But which category is the reference, it doesn't matter. Which one you denote as the last one, that depends on your coding, that's irrelevant. So what the baseline category model does is you model the log odds of observing outcome J instead of observing the baseline outcome capital J. And you model that, so this is like the logic of this odd over here, the odd of observing outcome J instead of the reference outcome. You model that just as a function of the linear predictors, where you have here an intercept and you have here the vector of covariance. Or equivalently, you can show that the previous expression is equivalently, it's obvious to see that the probability then of observing outcome J is the probability of observing the reference outcome, which in this case is the last one, times the exponential of the linear predictors. And obviously, when j is equal to the reference value, when j is equal to j, then this logarithm, this becomes 1, and then the logarithm becomes 0. The whole term here becomes equal to 0. So we are going to consider that alpha j and beta j for the category, for the reference category, are equal to 0. Now, there are a number of interesting things here that we need to take into account. You have to see that we consider different parameters for each logit. So in each logit, we have an intercept and we have a vector of coefficients. And this change with j. So when you use a different j here, then you will have different parameters to model that logit. And you actually don't need to come out with an expression for the probability of the reference category, because these probabilities, they sum until 1. So if you have an expression for the j minus 1 probabilities, then the reference probability, the probability for the reference category just come out of this equation over here. And this is our model. This is the baseline category model. What you do is you model the logit of the odds of each category with respect to the reference category. So you only need to model j minus 1 log odds. And that's the baseline category logic model. Now you can show very easily that based on the previous model, then the probability of observing outcome j is given by this expression over here. So the probability of observing outcome j is e to the power alpha j plus x transpose beta j divided by the sum, 1 plus the sum. And if you look at this, this is pretty much similar to what we saw in the logistic regression model. Of course, in the logistic regression model, we didn't have this sum over here because you only had 2 categories. But this is like the speed function. It looks really very similar. And we have the convention that for the reference category, the coefficients are equal to 0. Now, how you interpret the coefficient of certain variable, certain covariate xm? So the interpretation, for instance, of e to the power beta jm, and beta jm over here is the coefficient that accompanies covariate j here, when you write down this model. The interpretation is as follows. It's very similar to logistic regression. E to the power beta jm is the multiplicative effect of a 1 unit increase in xm, if xm is continuous, is the 1 unit increase in xm on the odds of response j in a state of response uh, j. And this j is the category, is the reference response, let's say. And to see that, you only need to go back to here, and then you write down this logic for x and this logic over here for x. You write down now the same logic, but when you have x plus 1, and then you subtract one of the other, and you will see actually what we are saying here. So that e to the power beta jm is the multiplicative effect, that what happened when you increase xm in 1 unit on the odds of response j instead of response j, where j, the second j, is the baseline category. Now, if you want to remove one variable from this model, then obviously you will need to make j minus 1 coefficients equal to 0, because for each logic, this covariate has a different coefficient, right? You see here that is beta j. So for each logic, you have a different coefficient. So if you want to remove the covariate from the model, you need to make all its coefficient equal to 0, and you have a different coefficient per logit, and you have j minus 1 logit, so you will have to make j minus 1 coefficients equal to 0. Now, as I said before, this model can also be used when you have ordinal responses, absolutely. But in such a case, you will be ignoring information about the ordering, and your results are going to be correct, but you may be losing power. So uh, you may miss certain effects just because you are not using all the information you have available. Now, I told you that which category is chosen as the baseline category is absolutely relevant. It's a completely arbitrary thing. And to see this, suppose that you have two categories, A and B, and you want now to calculate uh, the odds of category A instead of category B. How you do that? Well, you have the probability that you will observe outcome A divided by the probability that you will observe outcome B. That would be the odds of observing outcome A instead of B. If you calculate the logarithm of that, then you can show very easily that this can be written in this way. So that logarithm on the left side is just the difference between these two logarithms, the logarithms of observing, the logarithm of the odds of outcome A with respect to outcome J, and the logarithm of the odds of observing outcome B instead of outcome J. And now you can use the previous model, the model we introduced, and you can see that the logarithm of the odds of observing outcome A instead of outcome B is alpha A minus alpha B times the transpose of the covariance beta A minus beta B. So any of the categories can be chosen as a baseline category. And what you will see is that if you change the baseline category, if you change the reference category, the model fit is going to be the same. You're going to get the same maximized likelihood, and you're going to get the same fitted values, etc. The coefficients obviously are going to change because the coefficients are modeling the logarithm of the odds of observing certain outcome with respect to the baseline category. So if you change the baseline category, the coefficients, the alphas and the betas, are going to change, but they are differences. The alpha A minus alpha B and the beta A minus beta E, between any two categories, they are going to stay the same. So which category is selected to play the role of the baseline category is up to you, depends on the problem. In some problems, you may have a category that is naturally the reference. In other situations, that may not be, and you may not have a natural reference, and in that case, it doesn't matter which one you consider as a reference. When you compare two different categories by the logarithm of an odds, like here, this is not going to change irrespectively of the category that was chosen as the baseline category. You're going to get the same results when you compare the two different categories, A and B. Okay, so we have the model. Here is our model. Our model is given here. And now the question is, how can I estimate the parameters? How can I calculate confidence intervals? How can I do tests? And again, If you have these probabilities, we have a likelihood. We calculated a likelihood over here, a log likelihood. The only thing you need to do is you need to plug in here the previous expression. So if you plug this equation now, this pi j over here in your likelihood, if you plug it here, then you can apply all the machinery of maximum likelihood. You can calculate then the maximum likelihood estimates, you can calculate the confidence intervals, you can use the Holy Trinity, and all the theory we saw for maximum likelihood will be applicable here. Now, let's see an example. Let's see an example. It's easier to see all these concepts via example. What we have here is a study about the mental impairment of individuals. The data come from a study of mental health for a random sample of adults residents of Alachua County in Florida. And it relates the mental impairment to two explanatory variables. So we want to see the impact of two explanatory variables on the mental condition of these individuals. Now, mental impairment, which is my response variable in this case, impaired, is the response variable, but it has four different categories. Well, that we will call as one. That means the individual doesn't have any mental issue, he's doing fine. Mild symptom formation, that we will code it as 2. That means the individual, as the category says, has some symptoms, but these symptoms are moderate, are mild. Then we have moderate symptom formation. The individual has symptoms, but now they are a little bit more severe. They are not mild, they are moderate. And then we have the last category, number 4, which is impaired. And that means that the individual has some serious mental issues. So that's my response. And as you can see, now my response variable is not a binary variable, is a categorical variable. Now you can dichotomize this variable. You can create a new variable, mental impairment, that would take two values, well and not well. So the individual doesn't have a problem or the individual has a problem. But obviously you will be losing information there. We have more information than that. So we have a categorical variable. By the way, here mental impairment, you can argue that it's an ordinal variable because you can put a natural order there. You can say that, for instance, well is smaller than mild. So well means zero symptoms. That's smaller than some mild symptoms. That's smaller than moderate symptoms, and that's of course smaller than severe symptoms. So you can argue that here you have an ordinal response. But for the moment, we are going to ignore the order. For the moment, we are going to consider mental impairment as just a categorical variable. We are going to ignore the natural structure in that categories, which is the order. And then we want to see the impact of two covariates on mental impairment. The first one is an index, is a life index. And what is that? That's a composite measure of the number and severity of important life events that this person has suffered. For instance, like the birth of a child is an important life event. A new job is an important life event. A divorce is an important life event. For instance, if some close member of the family have died, that is an important life event. So this index is just a composite that measures the number of and severity of these important life events and measured in the past 3 years. And it's obvious, is reasonable to say that the number of life events will have an impact on the mental status of a person. And the other covariate we want to assess is socioeconomical status. And we are going to consider this covariate, we're going to code it as a binary outcome, as a binary covariate that takes value 1 or 0. And in this case, we are going to consider 1 for people people that have a high socioeconomical status, and 0 for people that have a low socioeconomical status. And it's also logical to think that the economical situation a person is in has an impact on the mental status, the mental impairment of an individual. Probably, I mean, if you don't have a way to pay your bills, that is going to affect you psychologically very seriously. So these are the two covariates. So here we have, this is our data set. So for instance, the first individual that we have here, well, here you have people with a low socioeconomic status, they have between 0 and 2 life events, and they are doing well psychologically. There are 4 individuals in this situation. If you look now, for instance, to this category over here, so these are individuals that have a low socioeconomic status. They have between 2 and 6 life events, and they are doing well. And we have no individuals in this situation. So they are not individuals with a low socioeconomic status, poor, with more between 2 and 6 life events, and have not mental issues that are doing well. No individuals in that situation, and so forth. So this is just a table showing a general description of the data. And now we are going to fit our baseline category model. And to do that, there are different functions that you can use in R. We are going to use the function VGLM. VGLM is a function that you can find in the package VGAM, and is really a very good function to fit all these type of models. You will see that it's very flexible, allows you to do a lot of things. So there are other ways to fit this in R, but I advise you to use this function. And here we have our model. So we are model mental impairment. In this case, it's called impair2 in the data set as a function of socioeconomic status and the number of life events. And you write here family multinomial. If you don't write anything else, then you are going to consider by default the logic link to model these odds, the odds of each category with respect to the baseline category. Of course, you can use other type of link function if you go back to the model, and we're going to see that later on. If you go back to the model, to the original model, here we use the logic transformation. You are modeling the logarithm of the odds of observing category J with respect to the baseline category. That's a logic link, but we will see later on that you could use other uh, links as well. So here we have, that is my model, and then if you don't put anything else, you put multinomial, then by default is the logic. And here we have the coefficients estimates. You see that now you have 3 estimates for the intercept, you have 3 estimates for the effect of socioeconomic status, and you have 3 estimates for the effect of life event. Why is that the case? Because we have 4, our categorical variable takes 4 different categories. You have you have mild symptoms, you have moderate symptoms, as you have impaired. Here, impaired is the reference category. So we have here 3 logics. You model is J minus 1, you have 4 categories, 4 minus 1, you need to model 3 logics. So you're going to model here, for instance, the logic of being well versus being impaired. Then you're going to model the logic of being mild versus being impaired, and you're going to model the logic of being moderate with respect to be impaired. Now, let's go back to the first one over here. So we are modeling, the function will give you here the logarithm of the odds you're modeling in this case. So well against impaired. So here you have the intercept, because for each logic we have different parameters. That's the baseline category model. So for each logic you have a different intercept, and you have different coefficients for the covariance. And then you see, for instance, that people that have a high socioeconomic status, where do you define the frequencies? The frequencies are not defined. The frequencies are observed. So the frequencies are just the ones that we observe. And this data set, what I showed you before was not the data set, was a table I constructed based on the data set. So what we have here, you see that the coefficient is positive, is 1.6. So that basically means that people with a high socioeconomic status, the odds for being well are larger than the odds for being impaired. That's what you have for here. But we are going to see the interpretation later on. So this will be the coefficients for the first model, for the log of the odds of being well versus being impaired. Then here you have the coefficients for the log of being mild versus being impaired instead of impaired. And then here you will have the coefficients for the log of being moderate instead of being impaired. So these are the three logs we are modeling. And here you have the residual deviance. The residual deviance has the same interpretation as we saw before. It's a likelihood ratio test comparing the fitted model with a saturated model. And if the model is approximately correct, you will expect these values to be more or less the same. Here you have also a message saying no Hawk donor effect found for any of the estimates. You can look in internet in Google for what this means. Basically, this means it's something that happens when some parameters in the model get close to the border of the parameter space. And when you have that, then you get a very weird phenomena. That is that when you do a wild test and your maximum likelihood gets further away from the value you're testing under the null, you go back to the first lectures, the first two lectures, when you have a wild test, if you remember what you do is you have your parameter estimates minus the value of the parameter under the null hypothesis, then you multiply that by the inverse of the variance covariance matrix, and then again, the parameter estimate minus the value under the null hypothesis. So somehow what you're doing is you're calculating the distance between the maximum likelihood estimate and the value of the parameter under the null. Now, typically, you would expect that if the maximum likelihood that gets further away from the value of the parameters in the null, then the wild test will grow, will become larger. And when you have this problem that some parameters start getting close to the border of the parameter space, then the wild statistics doesn't increase monotonically with the distance between the maximum likelihood and the value of the parameter under the null. And that is obviously an indication of a problem. And the problem is that some parameters are just close to the border of the parameter space. That's what happened, for instance, also when you have quasi-separation or separation in complete separation in logistic regression, where some probabilities are equal to 0, 1. So they are on the border of the parameter space. And when you have that, maximum likelihood doesn't work well, because maximum likelihood assumes to work fine that the parameters are not on the border of the parameter space. So you have a probability. That probability cannot be 0 or 1. If it is 0 or 1, maximum likelihood doesn't work. So that probability may be so close to 0 as you want, so close to 1 as you want, but cannot be 0, 1. Obviously, when it gets very close to 0 or very close to 1, you start getting problems with maximum likelihood. And in this case, no problem was detected, so we don't have that issue with this model. We will see later a case in which we do have an issue. So everything seems to be fine here. Now, here you have, these are the three models. So these are the coefficients for the intercept and socioeconomical status and life events when you model the logic of being well with respect to being impaired. Here you have the coefficients when you model the logic of the odds, the logarithm of the odds of being mild with respect to being impaired. And here you have the coefficient for the odds. So here you're comparing moderate with impaired. So we have different coefficients for each logic. That is what the baseline category model does. And as you can see, well, for instance, if you look at the socioeconomical status, you see that this coefficient is positive. So that means the odds of being well in a state of impaired are larger for people with high socioeconomical status than for people with low socioeconomical status. And when you look at here, the same happened. So you see that the odds of being mild in a state of impaired are larger for people with a high socioeconomical status than with a low socioeconomic status. And here, the opposite seems to happen. Here, if you look at the coefficients, but that coefficient was not significant, if I remember correctly, that coefficient was not significant here. Yes, it was 0.76, but we will test that later on. So if you look at the live events, you see that the coefficients are always negative. So that means that if you increase the number of live events, then the odds of being well instead of impaired will reduce. So the it's like your probability of being well decreases as you increase the number of live events. Now you can calculate confidence interval for all these parameters. Here the default, unlike in the classical logistic regression, in which the default to calculate the confidence interval is the profile likelihood method, here if you use the confint, the default is the wild confidence interval. Now we have seen that wild confidence intervals, they have some problems. They are not invariant to transformation. They can give you values of certain parameters that out of the range of the parameters. So for instance, a wild confidence interval for the probability can be negative, which is impossible. Profile likelihood is preferable because you would not have this type of problems. But if you want the profile likelihood confidence interval, you need to specify it yourself here with the method statement. So this is our model. We got our maximum likelihood estimates. Here you have, these are the three odds that we are going to model, the three logics that you're going to model. So the logic of wealth versus impaired, mild versus impaired, and moderate versus impaired. And here you have the three different models. We have different intercepts, different effect for socioeconomical status, and different coefficients as well for the number of life events. How should we interpret the parameters? This is the same interpretation as for logistic regression. At the end of the day, we are dealing with odds and logics here. So we are modeling the logarithm of the odds of being well versus impaired. And that's exactly the same interpretation. So how we will interpret this 1.61, for instance, is the coefficient for socioeconomical status. Well, essentially for a given number of life events, because we are adjusting here by life. So for a given number of life events, individuals with a high socioeconomical class, the estimated odds of being well instead of impaired are e to the power, the coefficient there. So e to the power 1.6 is 2.7. So for the given number of life events, for individuals with a high SS, the estimated odds of being well instead of impaired are approximately 3 times larger the estimated odds for people with low economical status. That's the interpretation. It's exactly the same interpretation as for the logistic model. The only thing is that you need now to take into account that you have three odds. So you're comparing here well versus impaired. And how you interpret then the coefficient of life, exactly the same as in logistic regression. Given socioeconomical status, because we have says in the model, given the socioeconomical status, one extra life event then reduces the estimated odds of being well instead of impaired in a 43%. That is just the interpretation. So the interpretation is very similar to the one we saw in logistic regression. The only thing is that you have here now three different logics because you construct three different odds. But the interpretation of each of this model is the same as for the logistic regression. You interpret it in the same way. We are talking about odds ratios here, and this is just the same interpretation as before. Okay, how can we evaluate the model? So here we could also, in principle, use a Pearson chi-square test, or we could use a deviant test. We could use the same type of techniques we saw before. Now, if you want to apply, for instance, a Pearson, you know that you need to have repeated measurements. You cannot have a continuous covariate, because if you have a continuous covariate, then you know that you will not have repeated measurements. Each vector of covariates will be unique. And in this case, if you consider you have a continuous covariate, which is the number of life events, and you may assume that you may not have repeated measurement for all the vector of covariates, because the number of life events for some individuals may be unique. You may have, I don't know, one individual that have 3 life events, and this is the only one. So what we did to try to solve that problem, we categorize the number of life events. We consider 2 categories to see if we can have repeated measurements now. So we consider between 0 and 4 life events, and between 4 and 9 life events. So what we're trying to do here is to try to categorize life event to be able to have more to have repeated measurements. And you do that, and then you have here, so what we are doing here is calculating the predictions of the model for the responses. So basically, we're calculating the probability of having each of these category, well, mild symptoms, moderate symptoms, or uh, uh, severe symptoms for each combination of the covariates that we have. And here you have the observed values. This is what we actually observe in the data set. For instance, you see that we have a for people with low socioeconomic status and they have between 0 and 4 life events. Well, in this category, low socioeconomic status and between 0 and 4 life event, we have 4 individuals that were doing well, 2 individuals that had mild symptoms, 4 individuals that have moderate symptoms, and 2 individuals that were impaired. That's the observed data. For instance, a people with a low socioeconomic status and they have between 4 and 9 life events. Then you have non-individuals, 0 individuals that were doing well, 2 were having mild symptoms, 1 was having moderate symptoms, and 3 were impaired, and so forth. That's the observed data. Now, what the model predicts for this table. So if you calculate that table now, but based on the model predictions, then this is the table that you get. And if you look at the table, you see that the model is not doing that bad. For instance, uh, the model predicts that with low socioeconomic status and between 0 and 4 life events, we should expect 3.5 individuals doing well. We should expect about 3 individuals doing mild symptoms, 3 doing moderate, and 2 individuals impaired. And here you have the observed value, which are relatively close to the predictions of the model, right? So if you have low socioeconomic status, but then you have between low socioeconomic status, but between 4 and 9 events, the model predicts, well, 0 individuals doing well, exactly what we saw with the data, about 1 having moderate mild symptoms. Well, in the observed data, this was 2. Here you have 1.5, about 2 with moderate. Here we got 1, and here 3 impaired individuals, 3 impaired individuals. So if you compare these two tables, you see that the model doesn't seem to be doing that bad. Now, you can now compare these two tables using the Pearson chi-square test, because here you have the observed frequencies, here you have the expected frequencies, the expected frequencies under the model. These are the observed frequencies, and you can compare the observed frequencies to the expected frequencies using the Pearson chi-square test, which is the observed frequencies minus the expected frequencies, and now you square that and you divide by the expected frequencies and you sum that for all the cells in the table. You can calculate the Pearson chi-square test, and if you do that, you get a p-value which is non-significant. So you get a very large p-value, which is about 0.95, so it's almost 1. Now, the test may not be reliable because the Pearson chi-square test, to be reliable, you should have all the expected frequencies should be larger than 1. And you see here that some expected frequencies are actually smaller than 1. So that may not be reliable. However, if I look at these two tables, I will not be extremely worried about the performance of the model. It seems to be doing well. And you see here that the p-value was indeed very large. Now, using this model, I can test for the effect of socioeconomic status, and I can test for the effect of life events. As I said, if you remove CES from the model, then you will need to make 3 coefficients equal to 0. So the null hypothesis here is that these 3 coefficients, let me go back to show you. So these 3 coefficients are equal to 0. That is what it means to remove CES of the model. So these 3 coefficients equal to 0 under the null hypothesis. Under the alternative hypothesis, not all of them equal to 0. And here the same for life event. And this is what we are doing next here. So we are just calculating now. Well, the model seems to be okay. We are testing the effect of socioeconomic status and the effect of life events, and you can see that socioeconomic status was non-significant. We got a p-value of 0.16, but life event was actually significant. We got a coefficient, a p-value of 0.03. Now, we are not using here all the information we have, because we are using this baseline category model, and that means that we are ignoring the order in the response. And if you do that, well, the model seems to be okay. I mean, it seems to be describing the data well. We got this Pearson chi-square p-value, which is large. Okay, we may have some issue. There was one expected value smaller than one, but I would not really feel very worried here. If I see this, the predictions of the model, they seems to come in agreement with the data, the p-value is very large, so I will not feel very worried about this model. The problem is that this model ignores the ordinality of the response. We are considering here well, mild symptoms, moderate, and impaired just as labels. And there is more information. These categories are order. So the next question is, can I take this order into account? Can I use this information when building up my model? And you can. And we are going to see two different type of models to take this into account. Now, in many situations, your response is going to be ordinal. When you have a categorical response, in many situations, it is ordinal. For instance, think about quality of life. So if you're doing a study in patients and you are measuring, or for instance, a study with all adults and you're measuring quality of life, you can quantify, you can categorize quality of life as excellent, good, fair, and poor. And in this case, yes, your response is obviously a categorical variable, but there is a little bit extra structure in these categories. There is a natural order. Excellent is better than good, good is better than fair, and fair is better than poor. Suppose that you're asking political philosophy, the political view that an individual has about the world. Well, you can classify that as people that are very liberal, people that are slightly liberal, people that are moderate, people that are slightly conservative, and people that are very conservative, for instance. And here, this is a categorical variable. You have these categories, but there is a natural order. You may say that liberal is larger or smaller, it doesn't matter, but there is an order regarding a political view. Liberal is larger than slightly liberal, and that's larger than moderate, larger than slightly conservative, larger than conservative. Or the other way around. In this case, the order is a little bit arbitrary, but there is clear an order in the data. When I say very liberal, larger than slightly liberal, doesn't mean that a liberal person is better than a conservative person. It's just that you can order this. There is certain degrees of liberalism, of conservatism, if you want. If you are studying, for instance, government spending, you may consider, well, too low, about right, too high. And here again, you have a natural order. Any categorization of an inherently continuous variable will become ordinal, right? So if you have a continuous variable and you categorize it using cutoff points, then you will immediately get an ordinal response. For instance, this is something that we do very frequently with BMI, which is your weight in kilograms divided by your size in meters square. This is a measure that we use to define obesity, and it's a very good predictor for your general health status. And typically what we do is we say, well, an individual with a BMI smaller than 18.5 is underweight. So it's a person that has an unhealthy weight, but unhealthy in this in the sense that it's too low. Then a BMI between 18.5 and 25 is considered normal. That's a healthy weight. So when your BMI ranges between 18.5 and 25. Overweight is when your BMI exceeds 25, but is still smaller than 30, then you are overweight. And when you have a BMI larger than 30, then you are obese. And some people define also that when your BMI is larger than 40, then you have what they call a morbid obesity. And that means you really, really need to do something about it because it's dangerous if you have a BMI larger than 40. So, and you would like to take this order into account when you're going to construct your model. Can I use a baseline category model with this type of outcome? Yes, you can, no problem. We did it. We did it with this mental impairment data set, but you are not using all the information you have. So in the next half of the lecture, what we are going to do is we're going to introduce two very nice models to analyze ordinal responses. But let's take a short break of 5 minutes. Okay, welcome back. So what we are going to do now is we are going to introduce our first model to handle this kind of ordinal responses. So to try to take into account the ordinality in the response variable. So suppose that you have a response y that is a multinomial, but now the categories are order. So we are going to claim that 1 is smaller than 2, is smaller than 3, is smaller than j. And so now these codes we're using, this 1, 2, 3, 4 until j, these are codes. The real variable represents something else, but we claim that they respect the order in the categories. Now, what is the cumulative logic models? Of the cumulative models in general, we're going to start with the logic. Well, the probability that the outcome will be smaller than j, what is that? Well, that is the probability that the outcome is 1 or 2 or j, right? So the probability that the outcome will be smaller or equal than j is basically the sum of these probabilities, right? Is the probability that that y will be 1, or the probability that y will be plus the probability that y will be equal to 2, and so forth until the probability that y will be equal to y. And this is the probability that y is smaller or equal than j. Now, note that the probability that y is smaller or equal than 1 is exactly the probability that y is equal to 1, because 1 is the first category. And notice that the probability that y is smaller to 1, that probability over here is smaller than the probability that y is smaller or equal than 2, right? It should be quite evident that that's the case. Why? Because if y is smaller than 1, then it certainly is smaller than 2. Now, you may have that y is smaller or equal than 2, but that is not smaller than 1. That will happen when y is 2, for instance. So you have also an order in these probabilities. So the probability that y is smaller or equal than 1, that's exactly the probability that y is equal to 1. And that should be smaller or equal than the probability that y is smaller or equal than 2, and so forth. And then the largest probability is the probability that y is smaller or equal than j, because that probability is exactly 1, right? Y goes from 1 to j, so the probability that y is smaller or equal than j over here, that probability is 1. And what the model does, basically, we model now the logic of having y smaller or equal than j. So that's why we call the model the cumulative logic model, because what we do is we kind of model these cumulative probabilities if you want. So what is the logic of having a response smaller or equal than j? Well, that's the logarithm of the odds of having a response smaller or equal than j. And what is the odds of having a response smaller or equal than j? That's the probability that the response is smaller or equal than j, divided by the probability that the response is not smaller or equal than j. That means that the response is strictly larger than j, and that for certain value of the vector of covariance, right? And here you have again like a logistic regression now, right? But a logistic regression that depends on j. So you're going to have here again several logistic regressions. So what we model is the logic of having a response smaller or equal than j, and this, what is the probability that y is smaller or equal than j, is the sum of all these probabilities. The probability that y is 1, 2 until j, and what is the probability that y is strictly larger than j, that is to sum these probabilities over here. The probability that y will be equal to j plus 1, j plus 2, and so forth. And here is my model. I'm going to model the logic of having a response smaller or equal than j. That is the cumulative logic model. Now, how we are going to model that? Well, basically what you're going to do could be better. There is a question there. Could be better express the ordinal as the error bigger than others. We will see that later on. About latent variables, we're going to see that later on. So let me go back. So here we have the model. We are going to model the logic of having a response smaller or equal than j as an intercept that is going to depend on j, as you can see, alpha j, then times the vector of covariance times beta. So now we have a separate intercept for each cumulative logic. And we are going to model, by the way, again, J minus 1 logics, right? So here we are going to have a different intercept for each cumulative logic. But, and this is something important, the coefficients of the covariance, the betas, are going to be the same for all J. So the same slope for all cumulative logics. The effect of the covariance do not depend on J. And why we do that? Well, you can motivate this model based on a latent variable model. The same way we motivated the different link functions using a latent variable model, we are going to use that here again to motivate this model. So if you assume the existence of a latent variable model, then you will see that the beta will be the same, that the beta will not depend on J. But again, you don't need to assume the existence of anything. You can just write down this model and you can say, this is my model, period. The same way you don't need to assume the existence of a latent variable to say, I'm going to use the logic link, or I'm going to use the probit link, or I'm going to use the complementary log-log link. You can just define, this is the link I'm going to use, and then you apply your generalized linear mix model. So once you use that link, you connect your mean with the linear predictor using the response function. That's the link, the inverse of the link you're considering. And then you define the distribution and period. You don't need to assume any latent variable. But the use of this device, this is a mathematical device, this latent model, is a nice way to deduce the different link functions. And here again, you can see that you can assume the existence of a latent variable, and the categorical variable you are observing is a discretization of this latent continuous variable. We're going to see the detail later on. And if you assume that, then you will see that is the model that emerges have a constant beta. What I mean by constant is this beta will not depend on J. Now, you don't need to assume that. You just can write down your model in this way. And this is the cumulative logic model, just like that. And it's a model in which you have an intercept that depends on J, but the vector of the coefficients of the covariance do not depend on J. Now, an advantage of this model is that the curve you're going to get for the probability of having an outcome smaller than J, they are going to be parallel for all values of the covariance. They will never cross. As soon as you have that these intercepts are ordered. But if you have that the intercepts are ordered, then you will have that these lines over here are going to be parallel. For every value of x, the probability of having a response is smaller or equal than 1. This probability is going to be smaller than the probability of having a response smaller or equal than 2, and this is going to be smaller than the probability of having a response smaller or equal than 3. And that's going to happen for all possible x values. If you take a different x value, you are going to have the same order, that the probability of having a response smaller or equal than J is smaller than the probability of having a response smaller or equal than J plus 1 for all vector of covariance X. And that's a desirable property. And you can get that if you assume that the betas are constant, that they do not depend on J, and that these alpha J's are ordered. If you consider different betas, if beta depend on J, if you have now, like in the baseline category model here, a beta J, then this property may not be true for all values of X. This curve over here may cross. And then you may get a weird situation in which the probability of having a response smaller than 2, smaller than equal than 2, is smaller than the probability of having a response smaller than equal than 1. And that doesn't make sense. So if you assume that the beta doesn't depend on J, and you are, the intercepts well, but the beta's not, then you don't get that problem. Then the probabilities will respect this natural order. That is what you could expect in this case. Okay, that's your model. Now, you can show that if that is your model, if you are using this model over here, if you're using this model over here, then the probability of having response J can be calculated in this way. So the probability of having response J can be calculated in this way. And once you have these probabilities, then how can I estimate the parameters? Well, once you have this probability, the only thing you need to do is you need to go back to the likelihood we saw before on slide 5. So you come back here, you plug these probabilities in the log likelihood, or in the likelihood is the same. Now you have here the beta parameters included and the alpha parameters, the alpha j parameters included. And then you can apply it again, all the machinery of maximum likelihood to get the parameters estimate. So how you estimate the parameters? Well, exactly in the same way we did before, maximum likelihood. The only thing you need to do is you need to plug in these probabilities in your log likelihood, and then you can get the maximum likelihood estimate for beta, confidence intervals, you can get the holy trinity, etc. All maximum likelihood machinery will do the job for you. Okay, now this model, the cumulative logic model, if you go to the literature, you're going to see that this model is sometimes called the proportional odds model. And the question is, why do they call it that way? Right? The cumulative logic model kind of makes sense, because if you look at the model, that's what you do, right? You model the cumulative probability, the logic of the cumulative probability, the probability that y is smaller or equal than j given the covariance. So that's the cumulative probability, the probability that you will get a response smaller or equal than y. You calculate the logic and you model that. So that explains why we call this the cumulative logic model. But if you go to the literature, you will see that sometimes they call it differently. They call it the proportional odds model. Why do they call it that way? Well, what the model does, well, basically the odds of having a response is smaller or equal than j, what is that? That's the probability that the response is smaller or equal than j divided by the probability that the response is larger than j, right? And this is equal e to the power the linear predictor, right? That's just a consequence of the model. Now, suppose you have two different vector of covariance. You have two different points. We can call it x1 and x2. Then the odds of having a response is smaller than equal than j for x1 divided by the odds of having a response smaller or equal than j for x2. So this is a ratio of odds. This is an odds ratio. This is an odds ratio for having a response smaller than j for two different values of the covariate. You can show that this is equal to this, right? So the odds ratio is going to be equal to x1 minus x2 transpose times beta. That is the odds ratio of having a response, a cumulative response smaller, the response is smaller or equal than j for two different values of the covariance. So the log, if you calculate now the log of these equations, if you calculate the logarithm at both sides, you see that the log cumulative odds ratio will equal what? X1 minus x2 times beta. That will be the log of the cumulative odds ratio. This over here is an odds ratio. If you calculate the logarithm, then the logarithm of the cumulative odds ratio will equal the exponent here, x1 minus x2 times beta. And what you can see here is that the cumulative odds ratio, the log of the cumulative odds ratio, is actually proportional to the distance between x1 and x2. So if you consider, if you think about the difference between x1 and x2 as a distance between these 2 points, then the log of the cumulative of ratio is proportional to the distance. And this proportionality constant here doesn't depend on j, doesn't depend on the category, will be the same for every j. And that's why, given that the proportionality constant doesn't depend on j, that is the same for all of these logics, McCulloch in 1980 called the model proportional odds model. From there comes the name proportional odds model. Basically, because the logarithm of the cumulative odds ratio for two different values of the covariate is proportional to the distance between the covariates. And this proportionality constant here, beta, is constant. It doesn't depend on J. And that's why they call it the proportional odds model. You can call it sometimes the cumulative logic model, is sometimes known as the proportional odds model. So you may have both terms in the literature. Now, I told you before that this model that assumes that assumes indeed proportional the odds uh, ratios, you will see that this model that assumes the same beta for all values of j can be obtained very nicely if you assume that there is some kind of latent process. So let's do that to obtain our model. Suppose that there is a latent variable. We are going to call it y asterisk over here. And we are going to assume that this latent variable underlies the outcome, the ordinal outcome we observe, the y. And so here you have your model, you have your latent variable y asterisk. Here you have your covariate, let's call that x covariate over here. And here you have a linear regression that link the response, your latent response to the covariates. So if you go back to the linear regression lecture, so basically what you say here, you have a covariate equal to x1, and you have that some values of your points are going to be smaller than the average. Some values of the response when the covariate is 1 is going to be larger than the average, but you do have an average response for x1, and that average response is just the point on the line. These days, that is the interpretation of the regression line, and the variability around that average is just a normal distribution. You model that using a model distribution. So basically, linear regression is a GLM model. So you need to do two things. The systematic part is the line. So how the average response depends on the covariate. And then the distribution part is how the responses varied around the mean. And that's what we do in linear regression with a normal distribution. Now, suppose that now you define cutoff points for this latent response. In this case, we are going to consider three cutoff, alpha 1, alpha 2, and alpha 3. And what I'm going to say is, now I'm going to construct the observed ordinal variable y using my latent response and the cutoff points. So if the latent response is smaller than alpha 1, then my categorical variable is going to take value 1. If my latent response is between alpha 1 and alpha 2, then y is going to be equal to 2. If my latent response is between alpha 2 and alpha 3, then y is going to be equal to 3. And if my latent response is actually larger than alpha 3, then my categorical response is going to take value 4. So basically, you can think, if you have an ordinal variable, you can think that this variable is actually a discretization of a continuous variable. Now, you know that any continuous variable, if you have a continuous variable, an observable continuous variable like BMI, and you categorize it, you get immediately an ordinal variable, right? That's a fact. So you have a continuous variable and you categorize it, then you get an ordinal variable. Now we are doing a little bit of this, the opposite. I have an ordinal variable, and then I'm going to assume that that ordinal variable emanates from certain continuous variable that I cannot observe, but I can imagine that it's there. I just didn't observe it. And then that I categorize that latent response variable to obtain my ordinal variable. Now, again, it's a mathematical device. I mean, not in some situations I can imagine that there is this latent variable, but it may not be obvious even what it is. Suppose that you have a category, an ordinal variable, an ordinal response, which is political view. And this political view is categorized as very liberal, slightly conservative, and very conservative. Now, I can assume that there is some kind of latent continuous, right, in the political opinion of people, and that when this continuous latent variable exceeds certain threshold, then I would say the person is very liberal. When this continuous a latent variable is between two certain cutoff points, I'm going to say the person is liberal only, and then when it's between other two values is moderate, and then when it's between other values or smaller than certain value, the person is conservative. But that's a mathematical device, and nobody says that it actually exists. But we can assume that there is this kind of continuous expressing the political views of somebody, and that what we observe is a categorization of this continuous variable, right? Because between the liberals, some people are a little bit more liberal than others. Between the conservatives, people are complex. So you can imagine that there is a latent continuous, and based on certain cutoff, you just categorize people in these different political philosophies. So that is what we are going to do. So basically here we consider only three cutoff points, but in general, you can consider that you have J cutoff points. So you have alpha 0, which is minus infinitive, and then you have alpha 1 that is larger than alpha 0, alpha 2 that is larger than alpha 1, until alpha j minus 1, and then alpha j that is plus infinitive. And you will observe that your ordinal variable is equal to j if and only if this latent continuous variable lies in an interval alpha j minus 1 alpha j. It's a little bit what we saw here for the specific case in which you have three cutoff points. Now, in statistics, such an unobserved variable is called a latent variable. Again, keep in mind, this is a mathematical device. You don't need this. It's nice because, as you can see, you can derive the model in a very easy way, but you don't need to assume that such a thing exists. Now, suppose that this latent variable exists, and suppose that this latent variable satisfies a linear model like the one given here. And well, the errors here, the residuals, epsilon, they have mean 0, and certain cumulative distribution f. It can be whatever distribution you want. Now, in the specific case in which the error follows a logistic distribution, then the cumulative distribution of a logistic random variable is the speed function. You have it over here, right? But f can be completely general. You don't need to assume that you have a logistic distribution for the residuals. Now, you have this model over here for your continuous variable, and now you're going to define a set of j cutoff points in this way. So alpha 0 is minus infinitive, alpha j is plus infinitive, and then you have all these j minus 1 points in between. And now we are going to claim that the ordinal variable take values j if the latent variable lies in this interval. And now, if this model is correct, you can say, well, what is the probability that my response, my ordinal response y, is going to be smaller or equal than j? Well, that's the probability that the latent variable is going to be smaller than alpha j, right? Now, the latent variable follows this model over here. So the only thing that I need to do now is to plug in this here. And once you do that, you get that then minus x transpose beta plus epsilon is smaller than alpha j. And then if you pass the order to the right side, what you get is that the probability that this probability, the probability that the ordinal variable is smaller or equal than j, is equal to the probability that the residuals are smaller than the linear predictor. And that is just the cumulative distribution function of the residuals evaluated in the linear predictor. And now you can see that you have obtained your model very nicely. So the probability that y is smaller or equal than j given the covariance is the cumulative distribution f, and this can be whatever cumulative distribution you want, evaluated in the linear function. And you see that the coefficients beta are the same. They do not depend on j. So you get these proportional odds models of this cumulative um, models in a very nice way, as the model emanates in a very natural way from this latent model we considered before. Even though you don't need to assume that this latent model exists, you can start directly here. You can say, I model my probability in this way, period. You don't need to assume that there is some latent model. Now, the inverse of the f function will be the link function. So if you calculate now the inverse of the f, what you will get is that the inverse of the f function evaluated in the probability will be equal to the linear predictor, alpha j times plus X transpose times beta. So the inverse of this cumulative distribution function will be your link function. And you see that when you deduce your model from this latent model, then the beta doesn't depend on Y. The beta doesn't depend on J. So you have the same covariance effect for all the J. And this is a very nice property because think about it. If you have the same parameters beta for regardless of the J you are using, that means that regardless of the cutoff points you use to chop up the scale to chop up your latent variable to construct your ordinal variable. So regarding of the way you use to categorize this latent variable, the effect of your covariance are going to be the same. So you have this latent variable and you categorize it using cutoff points. Well, the effect of the covariance are going to be independent on how you categorize this latent variable. So if you categorize it in 3 categories or you categorize it in 20 categories, it doesn't matter. The effect of the covariance are going to be exactly the same. It doesn't matter how many categories you create or how you construct that categories, which specific cutoff points you're using, the covariance effects are going to be the same. And a nice consequence of that is that it makes possible to compare estimates from studies that use different response scales. So suppose that there are two people that are studying the effect of gender and income on political view. For instance, you have two people, you want to study the effect of gender and income on political view. But how you define political view? Well, somebody defines political view as liberal, moderate, and conservative. And the other person defines political view as libertarian, liberal, moderately conservative, conservative, and very conservative. So the response variable in both studies are the same. Now, if you use this cumulative link model, this is the way you call it, the cumulative link model, then what you have here is that the effect of gender and the effect of income is going to be the same on both scales. Whether you consider only 3 categories or you consider 6 categories, the effect of gender and the effect of income is going to be the same. So we can compare the effect of gender and the effect of income from these different studies, even though they use a different response variable. Because if this cumulative link model holds, then the effect of the covariates are independent of J, are independent of how this continuous latent variable was categorized. Another nice property is that if you reverse the order, so you can say, well, liberal is larger than, or libertarian is larger than liberal, and liberal is larger than moderately conservative, and moderately conservative is larger than conservative. Well, if you reverse the order, you say that now conservative is larger than moderately conservative, and moderately conservative is larger than, I don't remember now what I said, moderately liberal, and that's larger than liberal. If you reverse the order, the coefficients will be the same. The only thing is that you need to change the sign of the betas. But you will get the same betas with a different sign, but the absolute value will be the same, and you will get the same standard error. Now, remember that if you fit this model, and you want to interpret the coefficients beta now in terms of the latent variable, then you need to use minus beta. Why you need to use minus beta? Because here is your latent model. Here is your latent model. In your latent model, you consider that the coefficient, you have minus x transpose beta. And that leads to this model here. So if you fit this model and you want to interpret the coefficients now in terms of the latent variable, you will need to calculate minus the value of the coefficients. And that's pretty much it. So if you assume the system of this latent model, then you can get very naturally the cumulative link model. And you can use any cumulative distribution F basically to construct your model. Now, if you use the logic distribution, so if you assume that your response variable over here follows the residuals over here follows a logistic distribution, then the cumulative the cumulative distribution will be the speed function, and then obviously you will get your cumulative link model will become the cumulative logic model. But you don't need to use the logic link. You can use any f-1 link function that you want. And this is a nice way to obtain the model, assuming the existence of this latent variable. And it has the nice interpretation that the effect of the covariates are independent of how you chop up the latent variable. How you construct the categories is irrelevant. If you define 6 categories of 3 categories, you will get the same effect for the covariates. That's a consequence of the model. Of course, if the model is correct, doesn't we will see later on that sometimes the model may not be correct. Okay, how to fit this model in R? Again, we are going to use the VGLM function. Now, I'm going to reanalyze the mental impairment study, but I'm going to take into account the ordinality. So I'm going to now define a new variable that I'm going to call impair3, in which I'm going to say, well, there is an order in these categories. So I have here my original variable and takes value between 1 and 4, and then here I put the levels. And what I'm doing here is I'm constructing an ordinal variable, and now I'm going to fit the model using the VGLM function. And the model is exactly the same as before. So you have now your ordinal response, and you're modeling that using a socioeconomic status and life event. But now when you define family, you say cumulative, parallel equal to true. That means that we are considering the same beta for all the logics. And then, well, here I'm not going to use the logic link, I'm going to use the probit link. And I fit it here with the probit link just to show you that you can use other link functions. You don't need to use the logic. You can use a probit model as well. And now I can fit my model. You can use just maximum likelihood, as I said before. Once you have the probabilities, you can plug it in your likelihood, log likelihood, and you can use all the machinery. And then as you can see, you get now 3 different estimates for the intercept. These are the alphas, right? And the alphas depends on the logic. So here you have a variable that have 4 different categories. That's also well, mildly symptoms, moderate symptoms, and then impaired. So you are going to model 3 logics. The probability of y is smaller or equal than 1 over here. The probit of the probability is smaller or equal than 1, smaller or equal than 2, and smaller or equal than 3. And you have then 3 different intercepts. But the effect of the covariates are the same for the 3 logics. That is, that's what you specify here when you put parallel equal to true. You have this proportional odds model. And as you can see, the coefficient of socioeconomical status was positive, and that basically means that people that have a high socioeconomical status tend to have a probability of y smaller than j larger than individuals that have a lower socioeconomical status. And remember that one is well. So the probability that, for instance, an individual will be well is the probability of y is smaller or equal than 1. That probability is going to be higher for individual with a high economical status than with a lower economical status. The probability that an individual will be well or will have only mild symptoms, that probability is going to be higher for individuals with a high economical social status than for individuals with a low social economical status. And the opposite happened for life events. So you see the coefficient of life events is negative. That means that the probability of if you increase the number of life events, you will decrease the probability of being well, of the probability of being well or mildly symptoms, and etc. But you get the same coefficients for the covariates for the 3 different logics over here. Why is a proportional odds model? Okay, so these are our estimates. Here you have the residual deviance. What is the residual deviance? Is again, it's a likelihood ratio test. Comparing what? Comparing a saturated model with the fitted model. Now, the saturated model, here you have that the residual deviance has 115 degrees of freedom, And so the model doesn't seem to be doing that bad. This is about 100 over here, 115. Now, from where come these degrees of freedom? 115. Well, is the difference in the number of parameters between the two models you are comparing. And which models we're comparing? We're comparing a saturated model. How many parameters a saturated model has? Well, a saturated model, we have here 40 individuals, 40 subjects. For each subject, we have 3 probabilities, right? A saturated model gives a different parameter to each of these probabilities here, right? It fits the data perfect. So we have 40 subjects, and for each subject we have 3 parameters. How many parameters the saturated model has? In total, 120 parameters. My fitted model, how many parameters my fitted model has? We have 5 parameters here. We have the 3 intercepts plus the coefficients for CES and live. So we have 5 parameters, 120 parameters for the saturated model, 5 parameters for the fitted model. 120 minus 5, these are the 115 degrees of freedom you get here. And that's the deviance test, just comparing the fitted model with the saturated model. And oh, sorry. Now here you have the exponentiated coefficients, that the exponentiated value for 0.68 over here, and if you exponentiate minus 1.2, minus 0.2, you get this value over here. Now this is not interpretable here. Typically, if you use the logic link, then when you exponentiate the coefficients, you get an odds ratio. But here we didn't use the logic link, we used the probit link. So you cannot interpret the coefficients in terms of odds ratio. So these exponentiated coefficients here do not have any nice interpretation. And if you remember well, in logistic regression, that was one of the reasons why we use the logic link, because when you use the logic link, you have this very nice interpretation for the coefficients. They are the logarithms of odds ratios. So if you exponentiate the coefficients, what you're getting is odds ratio. Here, I'll give you that exponentiated coefficients by default, but they actually don't have any clear interpretation. So you cannot look at them. So if you want to look at them, then obviously you will have to use the logic link. And how you use the logic link, so we're going to fit again the same model, parallel equal to true. So what we're saying here is the same beta for all the j's, but now we are not specifying the link. And if you don't specify the link, then R by default consider the logic link. So this is the code just to fit the logic cumulative model. And if you do that, well, here you have now the values. So here you have now the estimate for the effect of social economical status. Again, it's positive. So that means that people with a high socioeconomic status always have a larger probability of a response smaller or equal than J for all J than people with a low socioeconomic status. And the way we are coding the response, the lower the better, because 1 was well, 2 was mildly symptoms, 3 was moderate symptoms, and 4 was impaired. So people that are in a higher socioeconomic status always have a larger probability of being towards the lower end of the scale, which is good, than people that have a low socioeconomic status. And the opposite for life event is negative. So any increase in the number of life events will decrease your probability of being in the lower end of the scale. And now we are considered the logic link. So before, in the previous model, what we have here in the previous model, here in the previous model, we were considered the probit link for the probabilities, whereas now we are considering the logic link for the probabilities. Okay, so is this it's not the same model, we are using a different link. Here again, you have the residual deviance, and you see here, well, deviance obviously change a little bit because you're using a different model. The degrees of freedom stay the same, 115. Why? The saturated model, well, you have 40 subjects. For each subject, you have to model 3 logics, and a saturated model gives different parameters for every logic. So you have 40 times 3, 120 degrees of freedom for the saturated model. For the fitted model, you have 5 parameters, so 115 degrees of freedom. Here you have the maximized log likelihood value here, and now you have the exponent of the coefficients. And now you can interpret this in terms of odds ratios. These coefficients now can be interpreted in terms of odds ratio, the exponential of the coefficients. How you can interpret that? Well, here is your model. The probability of having a response is smaller or equal than y as a function of CES and life is this coefficient that depends on j, but then you have here the effect of socioeconomical status, which is the same, and here you have the effect of life events, which is the same. And these two lines are parallel here. So the probability, for instance, of having a response larger than 2, so that's the probability of having a mental problem, because 1 is being well. So the probability of having a mental problem, well, is this line for socioeconomical status equal to 0. That means for poor people, the probability of having a mental problem is going to be always larger than the probability of having a mental problem for people that are in the high socioeconomical status. And that's going to be the same for all life events, number of life events. So what is this coefficient over here? Well, if you exponentiate the coefficient of CES, you get e to the power 1.11. That's about 3. How is the interpretation? Well, the odds of having a response is smaller or equal than j are 3 times larger for people in the high class than for people in the low class. So the odds of having a small value, because remember that here the scale is constructed in such a way that small values are better, one is well. So people that have a high economical status, the odds of having a better response, a good response, is 3 times larger than the odds of having a good response for individual with a low socioeconomical status. And the same analysis, so the interpretation is basically the same as in logistic regression. If you exponentiate that, e to the power minus 0.32, then you get about 0.70. And that basically means that the odds of having, once you adjust by socioeconomical status, the odds of increasing by 1 the number of life events, well, the odds of people having a response smaller or equal than y for this amount of life events is 0.73. The odds of having a response of smaller or equal than y if the number of life events is increased by 1. So basically, increasing by 1 the number of life events reduces the odds of having a response smaller or equal than y 30%. Is the same interpretation as in logistic regression. So these are the implications of the model. Now you can calculate the confidence intervals like we did before. The default is again the wild confidence interval. If you want the better profile likelihood confidence intervals, you can obtain it as well. You just need to add this little piece of code. And now here you have the confidence interval for your parameters. And if you exponentiate these confidence intervals, then you will get the confidence interval for the odds ratios here. Now we can test now the effect of each covariate, and here you will see that something interesting happened. If you remember, when we ignored the order, we got a clearly non significant p-value for socioeconomical status. Now the p-value becomes very close to significant. It's equal to 0.06. Somebody asked, what is the interpretation of the alpha j's? Again, the alpha j's are like the intercepts. You know that you need to be careful with the interpretation of the intercept, but you can interpret the alphas in terms of the cutoff points. If you would like to think about this model as a model that emanates from a latent model, so if you would like to say that you have some kind of continuous variable that gives your mental status, and when this continuous value is smaller than certain value, then I would say you are doing well. When this continuous variable is between two certain values, I'm going to say you have mild symptoms. When this continuous values is between other two values, I will have you have moderate symptoms. And when it is larger than certain value, we say that you're impaired. If you like to think of this model in those terms, then the alpha will be the cutoff points for this latent variable. That would be an interpretation of the alpha. But typically, we have seen many times during the course, you do not interpret too much the intercept. You just look at the covariance effect. So you can see that taking into account the ordinality give you more power. So here we will get something that you can call a borderline p-value, whereas if you analyze the data using the baseline category model, then you really get a non-significant p-value for economical status. So you do gain something by taking into account the order. Now, there is also something, if you like to interpret these models in terms of the latent variable, then you can come out with a couple of very nice results. So suppose that you have this cumulative link model over here, where it doesn't need to be a logistic. You're considering just an F here. A different F can be a probit, for instance. And suppose that this model emanates from a latent model. So you're going to consider that your categorical variable here is a categorization of a continuous latent variable. Again, this is a mathematical device. You don't need to assume that, but it is sometimes nice to think about the problem in terms of this latent continuous variable that we categorize. Well, we assume then the validity of this model. You assume that you have this latent response variable, which is continuous and satisfies these linear models, and the residuals having mean zero and certain cumulative distribution F. If you assume that, if you assume the validity of this model, then you get your cumulative link model immediately with the same beta for all the J's. Now, suppose that you have a binary covariate. So a covariate that give you a group, for instance, can be a treatment covariate, or can be gender. Suppose that you have a covariate X1 that takes only two values, 0 or 1. And suppose that this covariate has certain coefficient we're going to call beta 1. Sorry. Now, conditional on all the other covariates, suppose that you want to estimate the probability that y asterisk 0 is going to be smaller than y asterisk 1. So basically what you want to see is I have these two groups, group 0, which can be a control, and group 1, which is, let's call it a treatment group, or males and females, whatever, but you have this group 0 and this group 1. And I want to estimate the probability, if I take two individuals randomly from these groups, I want to calculate the probability that the individual in group 1 is going to have a response larger than the individual in group 0, but at the latent level, right? We will call this probability gamma. And this is sometimes called, people call it the latent ordinal superiority. I want to see if at the latent level, individuals in group 1 tend to have larger responses than individual in group 0. Now, if you use the normal model, so if this F over here is just the cumulative distribution of a normal distribution, then you can show that you can calculate that gamma probability in this way. And if you assume the logistic model, so if you assume that this this error term here follows a logistic distribution, then you can show that the gamma follows this expression over here. And you can calculate these probabilities in R. You can use the function ordinal superiority, and you pass your model over here, and then you get the gamma coefficient over here. This is the gamma coefficient over here. You will get it for all the binary covariates, right? In this case, we only have a binary covariate, which is socioeconomical status. So you get that this probability is equal to 0.3, approximately 30%. That means that at any particular life event, for any number of life events, there is about 30% chance, 30% probability of having a higher mental impairment for people in the high economical status than for people in the low economical status. So what that means that there is a 70% probability that people with a high economical status will have a smaller mental impairment than people with a low socioeconomical status. And this is a nice interpretation. So you can calculate that really people that are in the higher economical class, they have a less chances of having mental problems than people that are in the low economical class. Now you get another parameter here, which is the delta parameter. I didn't define it here, but this delta parameter is the probability that this probability minus the probability of the opposite probability. I don't remember. You can look at it in the R help for the FICAM function, but this is the one that is mostly used, and it has this nice interpretation. So in is the probability that individuals in group one will have a larger outcome at the latent level than individuals in group zero. And in this case, it's 30%. So people in the high class have a 30% chances of having a mental impairment than the other individuals. A question. So is that interpretation the same as the odds of the baseline model? I don't see why the interpretation is the same as the baseline model. The odds of the baseline model. I really don't understand that question very well. So here you are interpreting this at the latent level. In the baseline model, you are not using the latent level. You're just comparing the odds for two different categories. Here, what we are actually calculating the probability that the latent outcome in one group is larger than the other group. So the interpretation will not be the same. Now, you can define also some kind of R square, some kind of coefficient of determination at the latent level. And how would you define this? Well, the coefficient of determination at the latent level will be given by this expression. So what you need to do is you need to estimate the numerator and the denominator if you want to calculate that coefficient. So basically is the estimated variance of the prediction of your model divided by the estimated variance of the outcome. That's what the coefficient of determination is. Now, the variance of the predicted values, you can estimate it as the variance of the linear predictor, something that you have. And the variance of the latent variable, you don't have it because you don't observe the latent variable. But you can estimate it as the variance of the prediction plus the variance of the residuals in your latent model. That's just a little bit of algebra. And if you use the standard logistic distribution, then you can show that the standard logistic distribution is like the distribution that produced the cumulative logic model, and the variance of the standard logistic distribution is given here. So you can calculate the coefficient of determination for the latent model. And what you get here is 0.22. You can ask that using this command in R. So the interpretation would be that at the latent level, your model will be able to explain 22 of all the variability mental impairment. Keep in mind that this is at the latent level. You need to be very careful here. It's like the previous discussion we had, the previous discussion about this probability, this gamma probability. This is at the latent level. It's not at the observable ordinal level. It's at the latent continuous level. So it's a nice parameter. You can interpret it in a nice way, but is a parameter at a level you never observe. And remember that this latent level may not even exist, but it's nice sometimes for interpretational purposes. But keep in mind that all this is at a latent level. It's at the level you do not observe. So this R squared, this coefficient of determination that we're getting here is not for the ordinal model. This R squared is for this latent model over here. So the model, socioeconomical status and number of life events, is able to explain, if you use the logistic distribution for the residuals over here, if F is just the cumulative distribution for the logistic distribution for the residuals, well, then this model can explain about 22% of all the variability mental impairment at the latent level, whatever that means. Then, how you can check the model fit here? Well, you can do a little bit the same as I did before. You can construct then the expected values for, we again dichotomize the life events as between 0 and 4 and between 4 and 9, just to be able to have these repeated measurements. And then here you have the observed data, and here you have the predictions of the model, And like for the baseline category model, you see that the predictions of the model are the expected frequencies based on the model are very close to the observed frequencies. And so again, I would not be extremely worried. You can do a chi-square test to check this here, but if you do that, you will see still we have some expected values smaller than 1, so the chi-square test, the validity of the chi-square test may be questionable because some of the expected values are smaller than 1, and they should be all larger than 1, preferably larger than 5, so the test, I mean, you need to be careful when interpreting the test. But the p-value will be very large, and if I look at these two tables, I mean, the model seems to be doing a good job. It seems to be um, uh, modeling the main features in the data. Uh, when we can get lack of fit, well, there are different reasons why you can get a problem with your fit. You may be using the wrong limb function. You may be omitting some important predictors, or, and this is very important, you may have a violation of the proportional odds assumption. So we are assuming that we have exactly the same betas for all the J's. That's an assumption, and this may not be true all the time. So uh, how can you check if your model is correct? Well, you can do what we did now. You can consider these expected values for the table. You can then see the observed values. You can compare the expected and observed values using a chi-square test. Sometimes, like in this case, you have this problem that some expected values are smaller than 1. Another thing that you can do is you can consider a more general model. For instance, you can consider a model that doesn't assume proportional odds, and then you can compare the model that assumes proportional odds with the model that doesn't assume proportional odds. And there you are testing the validity of the proportional odds assumption. Now, how can we extend this model to a model that doesn't need this proportional odds assumption? Well, as I said before, there are, I mean, if you, the problem with not assuming proportional odds, so you can in principle consider a model like the one here, right? So this is a model that doesn't assume proportional odds. So the coefficients, the effect of the covariance depend on J, right? And you can assume that, you can try to fit that model. The problem with that model is that then this curve over here, they are going to cross. They are not going to be parallel. And that means that, for instance, if you have an x covariate, a value for the covariate here, the probability that the covariate, that the y is smaller or equal than 1 is smaller than the probability that y is smaller or equal than 2. That's what you would expect, right? That's the logical thing. This probability over here, this probability should be smaller than this probability. And it happens here. But if you consider now this value for the covariance, then you see that the probability that y is smaller or equal than 2 is smaller than the probability that y is smaller or equal to 1. That doesn't make any sense. That doesn't make any sense. Now, that's the problem that you can have when you consider a beta that depends on J, is that then the curve for the probability of y smaller than equal than J are not parallel. And that means that you don't have this equality for all values of x. So this is what you would expect. You would expect that the probability of y is smaller than j is always, always smaller or equal than the probability of y is smaller or equal than j plus 1. You expect that to happen for all values of x. Well, if you don't have proportional odds, then this may not be true, and that's undesirable. You may get paradoxes here. You may get results that are they kind of do not make sense. Now, so that's the problem with the non-parallel models. Well, you have other problems. The number of parameters, of course, are going to increase with J. So the model will have more parameters that typically, but that's also the case for the baseline category models. The model will have more parameters. A model with more parameters is less parsimonious, and that means that The more parameters you have, the harder it becomes to fit the model. You need more data. Now, even if the proportional odds assumption is not correct, what that means? That means that you're going to get bias estimates, right? But bias estimates may still have a smaller mean square error. So because you are now having a lot less parameters, if you assume that the betas do not depend on J, if you assume the proportional odds assumption, you're going to have less parameters. So the parameters may be biased because the model is not correct, but they are going to be estimated with a larger precision. And if the bias is not that big, then you're going to be better off with the wrong model than with the right model. You know what I mean? So you may say, well, it's always better to have a right model. Well, no, because if you have a correct model and this correct model has a lot of parameters, okay, you're going to get unbiased estimate, but their variability is going to be huge. And you may be better off with a model that is a little bit biased, but has less variability. You can estimate it with more precision. So is the variability in effect, the question here, a very important point is this third bullet over here. Is the variability in the effects great enough to make it worthwhile to use a more complex model? Because maybe the betas are not constant. Maybe the betas indeed depend on J, but they are almost constant. They are very similar. And then you may be better off by just considering the proportional odds model, right? So these are important things to keep in mind. When you're using the proportional odds model, is that the model has a lot of nice properties. We saw it. It allows you compare studies, the effect of covariance in different studies that consider different ordinal variables to express the response, that categorize this latent continuous, if you want, in different ways. It allows you to do that. The model is more parsimonious, has less parameters. So you get the order in the probabilities. So the probability of y is smaller or equal than y is always smaller or equal than the probability of y is smaller or equal than j plus 1, right? And that's a nice property as well. So you may prefer to use a model with these nice properties, even if the proportional odds assumptions is slightly violated. Because we all know that if the sample size is large enough, you are going to reject almost any model, because we know that all models are just approximation. Now, there is something in between, and it's called the partial proportional odds model, and was proposed by Harrell in 1990. And this model can be written in this way. And as you can see, the proportional odds assumption hold for the covariates X, but they do not hold for the covariate set. So here you have some kind of in-between situation. It's an intermediate framework between the proportional odds model that assumes that the betas are the same for all the covariates, the betas are the same for all values of J, and the non-proportional model, the non-proportional odds model that assumes that the betas depend on J. Here you said that the proportionality assumption holds for some covariates, but it doesn't hold for other covariates. And this is what they call a partially proportional odds model. Okay, let's do this in R. How can I fit all these models? The first model I'm going to fit is the model that doesn't assume the proportional odds. So a model that considers that the betas change with J. And how you fit that in R? The only thing you need to do here is to write down parallel equal to false, and then you're saying to R, I'm going to have different coefficients for each logic. And if you do that, well, here now you have, of course, before we only have one coefficient for socioeconomical status, now you will have three coefficients, because the effect of socioeconomical status depend on J. So you will have one for J equal to 1, one for J equal to 2, and one for J equal to 3. And the same for the live events. Now you will not have one effect, but you will have three effects. Now, if you look at the effects here, you see they're very similar. So, I mean, maybe assuming that the Fed is the same will not be a problem. Now, if you look at socioeconomical status, you see a little bit more variability here. So maybe I would be better off here considering this partial proportional odds model, in which I will assume that the Fed of life events do not depend on J, but the effect of socioeconomical status depend on J. You can think about these things, but this is obviously, well, this is the non-proportional model in which all coefficients vary with J, with the logic. And well, now here you see the residual deviance, and we have now 111 degrees of freedom. Why? Well, this is the difference in the number of parameters between the saturated model. The saturated model have 120 parameters. We have explained that already. And the number of parameters in the fitted model. In the fitted model, now we have 9 parameters. 3 intercept, 3 effect for socioeconomical status, 3 effect for life event. And then 120 minus 9 is 111. Now this will be the non-proportional model. Keep in mind this model may be problematic because the probabilities, the curve for the probabilities may cross. So you will not respect this value for the parameters. Now, if you look at the model, you realize that you get here for the intercept 3, you don't get the set value, which is the wild test, and you don't get a p-value. And if you look at the Hawk-Donner effect, you get a warning. And that means the effect detected in the following parameters intercept 3. That is an indication that maximum likelihood is not working properly, and that means that some parameters here may be in the border of the parameter space. Some of these probabilities may be very close to 0 and 1. And that is the problem. I mean, when you do not assume proportional odds, you may get all this type of problem. These probabilities may not be ordered, it's a problematic model. So here you get this warning, like, maximum likelihood is not doing a good job here. Now, what you can do is you can then fit these partial proportional odds. And what you're saying here is, well, if I look at the coefficients of live events, when you don't assume, I think it's over here, when you do not assume over here, when you do not assume proportionality, if I look at the coefficients of live events, they are all very similar. Here I see more variability, but these ones are very similar. So it makes sense in this case to try to fit a partial proportional odds model. And what I'm going to do is I'm going to consider that the effect of life event is the same for all the logics. But I'm going to allow the effect of social economical status to depend on J. And so if you do that, then you get here that for socioeconomical status, you have a different effect. So you see that the effect is about 1 for y is smaller or equal than 1, but the coefficient is then about 2 for y is smaller or equal than 2. And I'm going to have exactly the same effect for the number of live events. So I'm assuming proportional odds for live events, but not for social economical status. And if you look at the model now seems to be doing fine. I don't get any more a warning for this Hawk-Donner effect. So the maximum likelihood seems to be working fine here. So here we have the 3 models. So here we have the model when you assume proportional odds. So the intercept varies for the different logics, but you get the same effect for the covariates, right? This is the proportional odds assumption. Here you have the response of the model estimates for the partial proportional odds model. So now the intercepts vary with the logic, the effect of social economical status vary with the logic, but the effect of life event is the same for all the logics. And then finally, here you have the estimate for the non-parallel cumulative logic model, and here now all the parameters varies. So you have different intercept for the different logics, you have different effect of CES and different effect of life, number of life events. So you have the 3 different models. Now, if you compare the proportional and non-proportional models, if you use now some kind of likelihood ratio test to compare these 2 models, you get a p-value which is about 0.7. So the non-proportional model doesn't fit the data better than the proportional model. You don't improve model fit by allowing all these parameters to change. And if you use the AIC to compare the different models, then here you see that the best model from these three models, this is the proportional odds model, the non-proportional odds model, and the partially proportional odds model. And you see indeed that the best one is the proportional odds model, followed by the partial proportional odds model, and the model that assumes no proportionality is actually the worst model. So in this case, I think the proportional odds models is doing a good job, followed by the partial proportional, and the non-proportional is the worst model. So you should not consider that model. Now, let me introduce another example, and is a sample about religious fundamentalism. And this is an example that has a couple of interesting features. So what we have here is we have a response variable, which is a religious belief, and we are categorizing that response in three different categories: a fundamentalist, a moderate, and a liberal. That's the three ways we are categorizing religious belief. And then we have region: Northeast, Midwest, South, and West Mountain. So the response variable is religious belief, is ordinal. We are going to code it as fundamentalist is 1, moderate is 2, and liberal is 3. So we're implicitly assuming that fundamentalist is a smaller than moderate, is smaller than liberal, but again, you can reverse the order. The important thing is that there is a natural order. So the proportional odds model is given here below. So the probability that y is smaller or equal than j is, you have an intercept for each value of j. So here you will have these two odds, and then you have the same effect for the coefficients for regions is the same. It doesn't depend on j. So the beta coefficients do not depend on j. We are trying to see if the religious belief vary with the region. This is in the United States. So we want to see if people in Northwest are more fundamentalist than people in the West Mountains, or people in Midwest are more fundamentalist or moderate than people in the South. So R1, R2, and R3 are indicator variables for the regions Northwest, Midwest, and South, respectively. So West Mountain is the reference category for the covariate here. And this is my proportional odds model. I'm going to try to fit that model in R. So how you do that? You use the GLM function. So here you have the response variable, cbind, the three response variables, and then here you have the dummy variables for the region, and then cumulative parallel true. So we are considering proportional odds. And so the model fit, you get two intercepts. You get two intercepts because you're modeling two odds. The probability that y is smaller or equal than 1, so that's the probability of being a fundamentalist, and the probability of being a fundamentalist or a moderate. I think if I go back, fundamentalist or moderate. Yeah. So here we have the coefficient for R1. So here you are comparing northeast with West Mountain, and as you can see, the coefficient is negative. So that basically means that people in northeast they are less fundamentalist than people in West Mountain. And then you have the second coefficient here is for the odds of Midwest. So you're comparing the odds of being fundamentalist or moderate. I think was the term fundamentalist. I forget the three categories. Let me check it again. Fundamentalist, moderate, and liberal. So people from Midwest tend to be they tend to be more fundamentalist than people from West Mountain, and the same for the South. Only people in the Northwest tend to be less fundamentalist. And I mean, because here the scale is constructed in such a way that small values mean more fundamentalist, larger value, less fundamentalist. So here you have your model. And if you look at the residual deviance, you see that there seems to be a poor fit here. You have 3 degrees of freedom, and the residual deviance is 98. This thing should be approximately equal as a rule of thumb. That's not a formal test, but it's a rule of thumb if the model is correctly specified. So there seems to be a problem. Now, you see what is the problem. So, for instance, consider the probability of y smaller or equal than 1 in northwest. What is that probability? 14%, right? That's the probability of y smaller or equal than 1. That means the probability of being a fundamentalist. That's 14% in northwest, and that's smaller than the probability of being fundamentalist in West Mountain. Why? Because that's 20%. So the probability of being fundamentalist in Northwest is smaller than the probability of being fundamentalist in West Mountains. Now consider the probability of being moderate or fundamentalist. So the probability of a y is smaller or equal than 2. Now in Northwest, that probability would be 14% plus 52%, that's 66%, right? But in West Mountain, that would be 20% plus 44%, that's 64%. And now the sign change. You see? So what that means is that probably the effect of region depend on J. Because when J is 1, then you have that this probability is larger in Northwest, sorry, it's smaller in Northwest than in West Mountain. But when J is equal to 2, then the relationship reverses. Now, this probability is larger in Northwest than in West Mountain. So the effect of region seems to depend on J if you consider 1 or 2. And that means the odds proportional assumption seems to be wrong. The effect of region depends on J, thus there is evidence against the proportional odds assumption. And what happened is, if you look at this, it seems that the data are more clustered around the center, the value of moderate, in the northwest than in the West Mountain. So if you see here, most of the individuals here are moderate. You have a 14% smaller, a 34% larger, right? Whereas in West Mountain, you tend to have more people at the streams. You have 20% that are fundamentalists, and you have 37% that are liberal. So here they tend to be more concentrated in Northwest at the center. In the West Mountain, you tend to have more weight in the streams. And that indicates that the proportional odds assumption is failing here. So the model is not doing a good job. The proportional odds assumptions is failing. So what you can do in such a situation is, well, you can try then to fit a model in which you do not consider the proportionality assumption. And if you do that, well, what you're going to have now is that the coefficients of the regions are going to depend on the odds. And you can see indeed that when you compare uh, nor, uh, northeast with West Mountain, you see that the effect change with J. When J is equal to 1, the effect is negative. When J is equal to 2, the effect is positive. So the effect indeed change with J. And that's what you see here. So the proportional odds assumption is not true in this case. And you can see now that when you look at the residual deviance, the degrees of freedoms are equal to 0. So this is a saturated model. And to see that this is a saturated model, you just need to look at the table over here. If you go here, you have the table. So you have here a 1, 2, 3, 4 regions. You have 4 regions. And for each region, you have 2 independent proportions here. The saturated model will consider two parameters for each region. Why? Because these sum 1. In each row, the probability is sum 1. 14 plus 52 plus 34, that's 100%. So you need 2 parameters for each region. You have 4 regions times 2 parameters. You will get 8 degrees of freedom. And if you look now at the model here, the model has indeed a, no, it's not this model. The model has, go back here, this model had 8 parameters. So this model has as many parameters as the saturated model. That's why you get 0 degrees of freedom. This is a saturated model. It will reproduce the data exactly. And this is the model that doesn't respect the proportional the proportionality odds assumption. So if you compare here then the two models, you compare the model, the proportional odds model with the non-proportional odds model, then now you get here a very significant p-value. Is the p-value you get here. So indeed, the proportionality assumption here is problematic. And then you get the coefficients that depends on the value of j. So here you have the coefficients. In the proportional odds model, you get the same coefficient for all the values of j. So these are the regions, the three coefficients for region, because you have four regions, so you need three indicator variables. And in the proportional odds model, they will be the same. But if you have the non-parallel model, then these coefficients will change depending on the value of j. So these will be the coefficients which you consider j equal to 1, and these will be the coefficients when you consider j equal to 2. Now, we have seen that, okay, you can do this. You can assume the non-proportional model, and then this is the model fit you get. Now, we have said a number of times that the non-proportional odds model is problematic to a certain degree. And one of the problems you may get is that this curve for the probability crosses. So you will like always this probability over here to be smaller or equal than the probability below, right? You will like the probability of y smaller or equal than 2 to be always larger or equal than the probability of y smaller or equal than 1. And the non-proportional odds model may not respect that for all the values of the covariance. So it's a model that can have some issues. So what can I do if I get evidence like here, like the proportional odds assumption is problematic? Well, you can use a non-proportional odds model, but we know that model may have some issues. So I'm going to show you now an alternative model, another model we can use in such a situation, and it's called the adjacent category logic model, ACL. And this model, what this model does, well, in the proportional odds model, what we do, or the cumulative link model, what you do is you model the, well, if you use the logic, then you model the cumulative odds. That's what you do. The probability of j is smaller or equal, y is smaller or equal than j. Now, the adjacent category model, what it does is it quantifies local association. So what you model here is the logic of having a response equal to j instead of having a response equal to j plus 1. So this is the odds of having response j instead of response j plus 1. And this is what you model with this model. That's why you call it the adjacent category model, because you are looking at these adjacent categories, the category j and the category j plus 1. And then you model that logic using this linear predictor over here. And so as you can see, you're assuming again here the same effect for all the covariates. So the odds uses adjacent categories only, whereas in the cumulative logic model, it uses the entire response scale. All values are smaller than equal than j. And here we just compare adjacent category. Category j with respect to category j plus 1. In the other, we compare all the categories smaller or equal than j with the categories larger than j. And so the interpretations here are again odds ratios, because we are using the logic model. We are using the logarithm of odds. So, but they will be local odds ratios. So you're comparing adjacent categories here. And you're assuming again for this model proportional odds structure because you have the same betas. But now is to model these adjacent categories only. Um, an advantage of this model, an important advantage of this model is that the effect in these per category logic models, like in this adjacent category model, the ACL, you can estimate these effects even when, well, in retrospective studies, like in case control study. That's also a property of the logistic regression model. You can estimate the parameters also with case control study. Now, what is a case control study? In a case control study, you sample X conditional on Y. So for instance, let's assume that you want to study the relationship between smoking and lung cancer. And what you do, a case control study, you consider a number of individuals with lung cancer and a number of individuals without lung cancer. And then you go back to see in the group with lung cancer, how many were smokers, and in the group and non-smokers. And in the group that didn't have lung cancer, how many were smokers and how many were not smokers. So smoking is the covariate X and lung cancer is the response Y. So here, what you're doing is the reverse process. You sample X given Y. And logistic regression is valid for this type of design. So you can analyze this using logistic regression and you're going to get correct estimates. The ACL model has that property too. So if you have a case control study and you fit this model over here, the ACL model, then you are going to get valid results. That's not the case for the proportional odds model. So the cumulative logic model cannot be used if you have this kind of case control data. So that's an advantage of the ACL model. You can use it with case control data, whereas the cumulative logic model, or in general, the cumulative link model, you cannot use it with case control data. That's an advantage of this model with respect to the previous one. Now, there is a nice theoretical result that was obtained in the mid 80s by Anderson. And what he said is, suppose that you have like a case control study. Suppose that you are sampling X conditional on Y, right? And Y is an ordinal variable. Now, if the distribution of X given Y follows a normal distribution with mean mu J, the mean depend on J, but the variance covariance matrix no, then he showed that the logic, so the logarithm of the odds of having outcome J with respect to having outcome J plus 1, this, this logarithm has the following expression, where beta J is the inverse of the variance covariance matrix we saw over here, then mu J minus mu J plus 1. And this is a nice theoretical result because it shows that if the means are equally spaced, so if the means, the mu j's are equally spaced, mu j minus mu j plus 1 is a constant that doesn't depend on j. If you have that assumptions, then the ACL model holds with the same, I mean, then the beta j's are the same for all values of j, so the ACL model holds. And this is a nice theoretical result. So the ACL and cumulative logic model with proportional, so if you have equal space means, then the proportional odds assumption for the ACL model is valid. Now, generally speaking, the ACL model and the cumulative logic models, they both use this proportional odds assumption, and they produce good fits in similar situations. So typically when one of them fits the data well, the other one tends to fit the data well. The advantages of the ACL model is that you can use it with case control data. That's not the case for the cumulative model. The advantage of the cumulative logic model, though, is, for instance, that you can have this interpretation in terms of a latent variable for the cumulative logic model. And that means that the effect of the covariance will be the same irrespectively of how you categorize this latent variable. So if you consider, for instance, liberal, conservative, and very conservative, or you consider very liberal, liberal, conservative, very conservative, the effect of the covariance will be the same. And that's a nice property of the cumulative logic model. You can also calculate this R square coefficient of determination of the latent level, this gamma coefficient of the latent level. So it allows you to do this kind of nice analysis, whereas the ACL will not allow you to do that. On the other hand, the ACL will be valid if you have a case controlled study, whereas the cumulative logic model will not be valid in that case. So it depends on what you want, it depends on what is what you want to do, etc. So if you compare now two different categories, so as I say, the ACL basically compare adjacent categories. You compare category J with category J plus 1, you compare category J plus 1 with category J plus 2, etc. Now, suppose that you can compare you want to compare category J, outcome J with outcome K. Well, this logarithm can be decomposed in this way, right? Can be decomposed in this way. And now you know that each of these logarithms follow, you have a model for each of these logarithm, this adjacent category model, right? So for each of these logarithms, you have this expression here. And if you plug in these expressions in each of these logarithms and you sum up, then you get that the logarithm of the odds of outcome j compared to outcome k can be decomposed in this form. You have here this sum for the intercept, that, and then you have k minus j times then x transpose times beta. So the model can be expressed in terms of a baseline category logic, actually, right? Because if you look at this expression here, you see that this is very similar to a baseline category model. If you consider now the category K as the baseline, this is a baseline category model. So the model can be essentially expressed as a baseline category logic model. And here you will have the probability of having y equal to j if you use that model. So let me show how this will work in another data set. This is a data set comparing the opinion of people about research with stem cells. And people, the answer, the response variable is that is, should you found, do you think that we should found a stem cell research? And then we have 4 different answers, possible answer, definitely, or probably, not probably, and then definitely not. So this is a kind of philosophical issue. There is a lot of ethical debate about stem cells research. And we want to see the impact of 2 covariates on this, on the opinions of persons about stem cell research. One covariate is gender, female and male, and the other covariate is religious belief. So the gender has two values, female and males. Religion belief, we are considering a categorical covariate, which is fundamentalist, moderate, and liberal. And we are coding gender for like 1 for females, 0 for males. And we're going to do something interesting here. If you look at the second covariate, religion, is an ordinal covariate. Now, you can consider, well, I'm going to consider religion as a categorical variable, so I'm going to consider 2 dummy variables, 2 indicator variables for it. But if you do that, you will be ignoring the ordinality, because religion is not just categorical. In this case, it's ordinal. So you may consider that fundamentalist is smaller than moderate, is smaller than liberal. So what we are going to do, and I'm going to discuss this a little bit deeper shortly, but what I'm going to do, I'm going to consider religious belief as a quantitative variable with 3 values. So 1, 2, and 3. 1 for fundamentalist, 2 for moderate, and 3 for liberal. And you may say, but that's completely ad hoc. I could consider 10, 10, 20, and 30. Yes, you could. And we're going to see a little bit later the consequence of that. So this is going to be now my ACL model. So I'm modeling here the odds, the logarithm of the odds of having response j in a state of response j plus 1. That, for instance, the odds of definitely found stem cell research with probably found stem cell research. Or, for instance, the odds of probably found, probably not found research, stem cell research with definitely not found stem cell research. That's your model. You are comparing adjacent categories all the time. So this one with this one, or this one with this one, or this one with this one. That's what the model does. And we are going to have a different intercept depending on J, and then the effect of a gender and the effect of religious belief is not going to depend on J. And we have seen that this is equivalent to fit in a base category logistic model in which you compare always with a reference category. In this case, I'm going to consider 4, definitely not found, and then the coefficients will be just given here. So you will have beta 1, but now multiplied by 4 minus j, and you will have beta 2, but now multiplied by 4 minus j. So it's equivalent to fit this model as to fit a base category logistic model with these coefficients. These two are the same. And then you consider definitely not found as the reference category, but you can consider another one. This is just the one we are considering. Now, I told you that we had here an ordinal covariate, and we decided to just give some scores to the different categories. Now, the treatment of continuous and categorical covariates is rather straightforward, right? If you have a continuous covariate, then it's a continuous, you plug it in your model the way it is. If you have a completely categorical covariate, then you use indicator variables. But the situation is less clear when you have an ordinal covariate. How should I include an ordinal covariate in my model? Well, you can say I'm going to consider that it is categorical, and I'm going to create my dummy variables, and I'm going to introduce my dummy variables in my model. And that's correct. But by doing that, you are ignoring the ordinality. So you are really not using all the information you have. So how can we treat ordinal covariates? Well, that's a little bit of a more tricky issue. One thing you can do is just what we did. You can assign an arbitrary score. For instance, in this case of religious belief, we consider 1, 2, 3, fundamentalist, moderate, liberal, 1, 2, 3. And by doing that, then you are really taking the ordinality into account, because 1 is smaller than 2 is smaller than 3. Now, the problem with this is that it is completely arbitrary, right? I could use 10, 20, 30 to 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 quantify, let's say, this ordinal covariate. Now, you can show that if for any equally spaced scores, so like here, you know, the 1 and 2, the distance, let's say, between 1 and 2 is the same as the distance between 2 and 3. Here, the distance between 10 and 20 is the same as the distance between 20 and 30. So if you use equally spaced scores for religious belief, irrespectively of which specific scores you use, if you use equally spaced scores, then they will all provide the same fitted values. And they will all provide the same test statistic for the fit of religious belief. So if you're using equally spaced scores, it doesn't matter which scores you're using. Actually, you're going to get the same model fit, and you're going to get the same results for your test. Now, if you decide to use unequal spaced scores, for instance, you may what you are doing when you're using equally spaced scores is basically what we are saying here is that the distance, to put it somehow, the distance between a fundamentalist and a moderate is the same as the distance between a moderate and a liberal, whatever that means. That's a little bit of what we are saying. The distance between a fundamentalist and moderate is the same as the distance between a moderate and a liberal. And that's what you are assuming when you use equally spaced scores like here. Now, if you assume that the distance between a fundamentalist and a moderate is the same as the distance between a moderate and a liberal, then you can use here whatever scores you want that respect that property, so that the distance between 1 and 2 is the same as the distance between 2 and 3, or like in the other example here, the distance between 10 and 20 is the same as 20 and 30. So if you think that this is a reasonable assumption, then it doesn't matter which scores you use, you're going to get the same results, the same model fit, and the same result for the test statistic. Now, sometimes it may be reasonable to consider unequally spaced scores, because you may consider that the distance between a moderate and a fundamentalist is larger than the distance between a liberal and a moderate. You may consider that. If you think that, then you need to use unequally spaced scores. So instead of 1, 2, 3, you may consider here, I don't know, 1, 2, and 4, because the distance between a moderate and a fundamentalist is smaller than the distance between a moderate and a liberal. If in that case, then the results, of course, may change. It's not like before that it will not depend on the scores. Now, if you consider different scores, you may get different results. What you can do is some kind of sensitivity analysis. So you consider different scores and you look at the results. And what we have seen is that usually the substantive results do not depend so much on the choice of the scores, unless you have data that are highly unbalanced. But in general, you will see that the results are more or less, at least, how can I say, qualitatively consistent. So if the result, if the covariance is significant, it will stay significant with different set of scores. typically that's what you will observe, and you can have here the reference for this discussion. But it's an interesting thing because typically we know what to do when we have a continuous variable, what to do when you have a categorical variable, covariate, but how should we treat ordinal covariates? And well, you can always consider religious belief as a categorical covariate, but then you will be you will not be using all the information you have about religious belief. Okay, so let's fit this model, the ACL model. How you fit that in R? Well, we're going to use again the VGLM function. Now you use family equal to, yeah, the ACAT here. That's the code to fit an ACL model. And you have here reverse equal to true and parallel equal to true. Parallel equal to true means you are going to consider the same betas. The betas will not depend on J. And if you put reverse equal to false, then the only difference that you're going to be modeling the odds of the probability of J equal to y equal to J plus 1 divided by the probability of y equal to J. And if you put that equal to true, you're model the reverse of that. So the probability of y equal to J divided by the probability of y equal to J plus 1. So the only difference is, the only difference would be if you're going to be modeling this ratio over here, or if you're going to be modeling the inverse of this ratio. But for the rest is the same. So here you have your model, and that's the way to fit it in R, and these are now the results that we get. And as you can see, the effect of religion is positive and is highly significant. And that means if we see how we code it religion, 1 is a fundamentalist, 2 is moderate, and 3 is liberal. So that means that more liberal people tend to be more supportive of stem cell research. That's basically what it means. And you see that the effect of gender, and that is a little bit surprising, the effect of gender is negative, but was not significant. But that tends to indicate that women tend to support less stem cell research than men. And I mean, remember that here we are comparing always, we are always modeling and comparing category J with category J plus 1. And lower J's are supporting stem cell research. Larger J's means definitely not supporting that, not funding that type of research. So more liberal people tend to support more stem cell research. They will be more partidary of funding this research. More conservative, fundamentalist religious people will be against funding stem cell research, which is quite logical. And women, for some reason, tend to support that less than men, even though the p-value was not significant. And here you have the residual deviance, which is pretty much similar to the degrees of freedom. So the model seems to be doing a good job. And here you have the um, the fitted values. And you can see, for instance, what you have over here, Y1, remember, is definitely founding stem search, stem cells research, and then Y equal to 2 was probably founding it. The other one was probably not founding it, and then Y4 is definitely not founding it. And here you have, for instance, if you look at people that are fundamentalist, males and females, you see indeed that males tend to support more founding stem cell research than females, a little bit, a little bit more. And you see that males, they the probability that a male will say definitely not founding is smaller than the probability of female. So males in the fundamentalist group, even in the fundamentalist group, males tend to be more favorable to stem cell research than females. And in the liberal group, you get exactly the same. In the liberal group, males tend to be more favorable about funding stem cell research than females. I really don't have a very good explanation for that. I don't know. Um, I really don't know. I mean, my only explanation is a stem cell research. Well, stem cells are these cells that actually are not specialized yet. So these are the cells we use to construct the human being. These are the cells that we construct. They later, I mean, when the women get pregnant, and these process, these divisions of the cells start, these stem cells are used to construct organs and to construct, and they are very important because they can be transformed in any cell. So that's the way we construct the human being. These cells start specializing, and then you get a stomach, or you get a brain, or you get eyes, right? And people want to do research of that because they think that these cells can be used in medicine. They can be very valuable in medicine. I don't know why women will be particularly against that. I don't know if it has something to do with the fact that, I don't know, that they carry babies. I don't know, but it's what the data seems to suggest here. On the other hand, if you look now, for instance, at males, but you compare fundamentalist religious males with liberal males, then you see indeed that liberals are males strongly support stem cells research, whereas fundamentalists no. And the opposite. So 16% of males in the fundamentalist group will claim, definitely, I don't want this to be founded, whereas only 5% in the liberals will claim, I definitely don't want this to be founded. So here you see the differences between the two groups. And the same for females. Fundamentalist females tend to be pretty much against founding this. Liberal females tend to be a lot more favorable to founding this. And here we have our model, our fitted model, with the effect of gender and religious belief. And so, for instance, for if you look at the coefficient of religious belief, which is 0.3 approximately, then you see that for moderates in both group, moderate is when R is equal to 2. The estimated odds of definitely founding uh, versus probably founded is e to the power 0.2. That's 1.3 times the estimated odds for fundamentalists. So liberals tend to be more supported than fundamentalists for both genders. It's something that we saw uh, in the previous slide. And you see that moderates, which is when R is equal to 2, the estimated odds of definitely founding stem cell research, J equal to 1, versus definitely not founding stem cell research, J equal to 2. That will be, well, 4 minus 1 is 3, 3 times the 3 times 0.26, the exponential value of that, that's 2.2 approximately. So would be about 2 times the estimated odds for fundamentalists of each gender. And that would be the interpretation of the model. So here, the saturated model, I mean, what about the model fit? Well, we saw that the residual deviance was more or less equal to the degrees of freedom, so we would expect the model to be fitting well. The saturated model, in this case, describes 18 multinomial probability, 3 for each religion and gender combination, because this probability needs to sum 1. So the model we have here, you have the deviance. The deviance was 11.99, and the degrees of freedom. Well, my model had 5 parameters. The saturated model has 18 parameters, so with 13 degrees of freedom, and in this case, the probability was 0.53. And this is a reliable test because here we have only categorical variables, so we know that we don't have any continuous variable. This is going to be fine. And if you apply here the cumulative model, the cumulative logic model, instead of the Jackson category, you will get pretty much the same results. Of course, the coefficient of religious belief will be larger because now you're modeling not comparing J with J plus 1, but comparing all values smaller or equal than J with the probability of having a Y greater than J. So the effect increases, but substantively, you get again a significant results for the um, effect of religious belief and gender. Like for the cumulative model, the ACL model assumes these proportional odds. So we are still making that assumption here. You could consider an ACL model that doesn't assume proportional odds. You could consider that the beta j's here vary with that the betas vary with j, so that you don't have a beta for all the j's, but that the beta varies with j. Um, the advantage is that now this model, unlike with the cumulative model, because in the cumulative model, if you don't have, if you have a non-proportional odds model, you have this problem with the probabilities, that the probability of y smaller or equal than 2 may be smaller than the probability of y smaller or equal than 1, and that's a structural problem because that cannot be. Well, here you don't get that problem. So a non-proportional model makes more sense if you're using an ACL model than if you're using a cumulative model. But the cumulative model, immediately you can get into that problem that the probabilities are not ordered in the way they should be, whereas here you don't have that problem. Uh, of course, yeah, if you consider this, you will have a less parsimonious model, but I mean, you can still use your model. So you can relax this non-proportional odds assumption here, and it's less problematic to relax it here than to relax it in the cumulative model. Let's do that. So if you want to do that, then the only thing you need to do is to put here parallel equal to false. And in that case, of course, you are going to get now different coefficients for each logic. You're going to get it for religion and you're going to get it for gender. So now, for instance, that would be the coefficients of religions for each of the three logics when you compare 1 with 2, 2 with 3, and 3 with 4. We are comparing here always adjacent categories. So 1 with 2, 2 with 3, and 3 with 4. And now you will get different coefficients for each of these logic. Yeah, they don't look that extremely different. You could test this model, and then you get the same three different coefficients now for gender. For the three logics, you get a different coefficients. And if you compare the two models, so the non-proportional model with the proportional model, you get a p-value that is non-significant. So this is it. The last two slides is just general information about still possible extensions of these models. I told you about that. For instance, in the logistic regression case, we saw quasi-likelihood methods. Can I have quasi-likelihood methods here too when my response is not a binary variable, but is a categorical variable or an ordinal variable? Yes, you can have also some kind of quasi-likelihood methods here. They are called generalized estimating equations. You can extend these to ordinal responses, for instance, such as the cumulative logic model. But we are not going to see that. If you want to use this type of model, there is a package in R. It's called multivariate GEE, and you can use that to do this kind of generalized estimating equations here. So you will not assume any multinomial distribution. You will specify the 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 mean structure, and then you will just use certain covariance variance function like we did in logistic regression and the Poisson regression, but this variance function doesn't need to be correct. There is also something that is called random effects model. We are not going to use these, we are not going to see this type of models, but if you have, for instance, longitudinal data and your response variable is ordinal, so you're measuring patients repeatedly over time, and in each time moment, you get a response about symptoms or quality of life, and quality of life may be excellent, more or less, and bad, for instance, and you're measuring this quality of life repeatedly over time, then you can extend these cumulative link models we have seen today of these proportional odd models, but now you need to include random effects. And that can also be done. There is a function in R called the CLMM that is in the ordinal package that you can use to fit cumulative logic model with random effects. But again, we are not going to see that. So which model to use? Should I use a nominal, a baseline category logic model? Should I use a cumulative model and adjacent category models? It depends on the data. some models will be invalid with some type of data. So if your variable is, for instance, really if you're trying to use a cumulative proportional odds model, but the proportionality assumption is not correct, then yeah, you should not use that model. You should use an adjacent category models with not proportional odds, or you should use, for instance, um, you can use a baseline category model then, or you may use a partially non-proportional odds model. So sometimes the data will specify which type of model you have to use. If your response, for instance, is not ordinal, then obviously you cannot use these cumulative link models. You will have to use a BCL model. And if you if you can use different models, like for instance, you may have a situation in which you can use the ACL model or you can use a cumulative link model. Which one should you use? Well, then you need to think about, yeah, what you want to do. For instance, do you want a connection with an underlying latent model? Do you want to have that interpretation? Well, if that's what you want, if in your concrete problem you see, well, it is an advantage if I can interpret my results in terms of a latent process. That may be the case, for instance, in psychology. Very frequently you work with these latent variables. Then you may prefer the cumulative link model than the ACL model. If, for instance, you have a case control study, then you know you cannot use the cumulative link model. You need to use an ACL model, etc. And finally, well, this FIGAM function in R is really extremely flexible. You may want to have a look at it. It allows you to do a lot of things. So just go there and have a look. Well, this is it. My apologies. I'm 4 minutes over time, but it's a lot of material that I wanted to cover today. This is the last lecture of the course. I hope you really found it useful and that you have learned a little bit about GLM, but also a little bit about statistical in general. And don't forget to work on the project next week. We will have a Q&L function, a Q&L session in which you can ask me general questions about the course and about the project. Please take into account that I need to be careful when you ask me things about the project. The project SAM is part of the evaluation, so my level of input here needs to be limited because the idea is that you work on this and I evaluate what you do. So thank you very much for being here today, and I will see you back next week.